Welcome to the C2B Independent Learning Resource produced by PIXL. This is a resource suitable for students taking the higher tier GCSE mathematics exam. It's for students predicted a secure C grade, known as a C1, and are targeting a B grade. Also for students who are predicted a C2, C3 or D1 and are targeting a C grade but are interested in completing some B grade topics. 8 key topics have been selected for this resource and they have been divided into 4 sections: number, algebra, data and shape. After each session there will be an assessment, and embedded along with the resource are functional questions. So the first topic we're going to look at is number. Within this we're going to focus on standard form and percentages. Listed here are the aspects we're going to be covering in standard form and the percentage change. So first off, why would we use standard form? If we have a look at these numbers here on the screen, they're really quite big. So we've got the number of atoms in a mole, as you can see, lots and lots of zeros there. How would you even say that number? Same thing, the diameter of an iron atom, really, really small. Again, here you're looking at these numbers. So we use standard form as a way of writing these numbers more easily. And what we need to be able to do is to write these numbers in a particular way. So, the first 2 numbers we have here are examples. 2 multiplied by 10 to the power 15 and 1.5 multiplied by 10 to the negative 12. Both of these numbers have been written in standard form. As you can see, there are 2 parts. First, here, the number between 1 and 10. We can see in our first example the number 2 and our second example the number 1.5. And then both of these numbers are multiplied to a power of 10, always 10. So we have a positive number here, 15, and here a negative number, minus 12. And we'll look at a moment as to what the differences are between those two. This way of writing a number can also be called standard index form or scientific notation. So given what we've just said, the number needs between 1 and 10, and then multiplied by a number to the power 10. Let's look at these 4 examples here on your sheet. I want you to have a think, 30 seconds, which one of these numbers is not in standard form? Okay, so we've got 4 numbers here. Let's take a look at the first one. 40 multiplied by 10 to the power 4. The second one, 7.3 multiplied by 10 to the minus 5, 3.57 multiplied by 10 to the power 7, and lastly, 3.58 multiplied by 10 to the negative 2. Looking at those numbers, the first number here is not in standard form. 40 is greater than 10. Remember, this first number must be between 1 and 10. So we can use standard form, as we saw at the beginning, to write really, really big numbers. This here is the mass of the planet Earth. As you can see, it's a big number, very long to write down, so we use standard form. Looking at the number, we need a number between 1 and 10. I want you to write this on your sheet as we do it. So we're looking here, we've got 5, 9, 7. So this number here is going to become 5.97. That's the only way we can make a number between 1 and 10. Our other options would be 59.7, too big, or 597, also too big. So this here is where our decimal point goes, you see on the screen here. We then need to multiply by 10 to the power. Where does this 24 come from? Well, if we have a look here, and we've got our decimal point that we've decided to put here, it actually started here. So if we count along, every time we're going to get to 24, and it's a positive number. Okay, so if we have a look back at the beginning, those 4 numbers we saw, what I want you to do on your sheet now is to have a look at the 2 big numbers, the first one and the last one, and I want you to write them in standard form for me now. Off you go, 1 minute. Okay, so if we just look at the first one together, our first number here, a number between 1 and 10, is going to have to be 6.02 multiplied by 10, and then we need to get this power here. If you count along, you should have the power 23. And our last one down here, which is also a really big number, so it's going to be a positive power, is 2.5284 multiplied by 10 to the power 11. Okay, we're going to come back and have a look at those smaller ones after we've had an example. So what I want you to do now, you've got 3 minutes on your sheet. You've got 5 numbers that are really big, you can see here, that I want you to have a go at writing in standard index form. Off you go. Okay, let's see how you got on with those. So if I can reveal the answers here, our first one, 8 times 10 to the power 7. Our second one, 2.3 times 10 to the power 8. 7.24 times 10 to the power 5. 6.003 times 10 to the power 9. Remember to keep those zeros in. And lastly, 3.7145 times 10 to the power 2. So that's writing large numbers that are ordinary numbers into standard form. We're going to have a look now together at writing small numbers. So we can write very small numbers using negative powers, okay? Just make that clear. You might want to underline that on your sheet as well. So we've got a really small number here, 0.00013 metres. We can see here our number goes to 1.3, a number between 1 and 10, and our power is the -4. Let's have a look at this together. Our decimal point starts here, and we're going to move it 1, 2, 3, 4 places, and that's where the -4 comes from. So I want you to go back to the beginning now and have a look at those questions that we had, those 4. Have a go at the 2 on the small numbers. So back to the beginning now, we're looking at those 4 numbers we originally saw. The diameter of an iron atom is going to be 7.4, our number between 1 and 10, multiplied by 10. Immediately, I know it's going to be a negative power, so put your negative in, and it's to the -11. And the wavelength of a red light, similarly, 6.5, our number between 1 and 10, multiplied by 10, again to the negative power, it's a small number, to the -7. Okay, I'm going to get you to do some now. So if you turn over your page, you will see this here. On here, I've got 5 examples, all really small numbers that you're going to write now in standard form. 3 minutes, off you go. Let's see how you've got on with those. So our first one, 6 times 10 to the -4. Second one, 7.2 times 10 to the -7. Our third one, 5.02 times 10 to the -5. 3.29 times 10 to the -8. And 1.008 times 10 to the -3. All negative powers, small numbers, being converted into standard form. Let's just recheck. Have a look at all of those numbers on the left-hand side. 6, 7.2, 5.02, all numbers between 1 and 10. If it's not between 1 and 10, the number is not in standard form. So we've gone from normal numbers into standard form. What we're going to look at now is converting in the other direction. You're going to be given a number in standard form and you're going to have to convert it back to a normal number. I'm going to ask you now to have a go straight away. 6 questions on your sheet. Have a go applying what we've just done, numbers from standard form into normal numbers. 3 minutes, off you go. Okay, so you've just been looking at converting back to normal numbers. If we look at our first one, make a decision. Is it going to be a big number or a small number? Look at the power, positive 6. Immediately you know it's going to be a big number. So our first one is actually 7,100,000. I'm just going to reveal the answers to the other ones. I want you to have a quick check of those yourself. Looking for negative powers, smaller numbers, positive powers, bigger numbers. So just have a mark through those, check that you've got those right before we move on to some calculations. So I've got one more activity for you to do, just to check that we're all okay with this. It's the matching activity. On the left-hand side of the page, you've got 7 numbers that are just normal. So if we look here, all of these blue numbers on the screen are your normal numbers. What you need to be able to do is match those with the numbers on the right-hand side, which are the same numbers just expressed in standard form. Again, the first number between 1 and 10 multiplied by the power of 10. Okay, I'm going to give you 4 minutes for this, matching them up using normal numbers and standard index form. Off you go. Let's have a look how you've got on. So the first number we're going to take together is 0.081. I'm just going to move it here into the middle. It's a small number, so we're going to have a negative power. Our decimal point starts here. We're going to have to move it to the right 2 times to make 8.1. We're going to have twice, therefore we're going to have 8.1 multiplied by 10 to the negative 2. The next number, let's take a big number here. 810,000. Positive power we're looking for, it's a big number. Our decimal point starts here and we move 1, 2, 3, 4, 5. 5 places, positive. We're going to have this one here. 8.1 times 10 to the power 5. Let's move these out of the way. Another big number, slightly smaller than the number we had before. 81,000. So positive power again. Our decimal point starts here. And we're going to move 1, 2, 3, 4. 4 places to the right. So we're looking for here 8.1 times 10 to the power 4, positive 4. A really small number we have here. If you count along, we're going to have 8.1 times 10 to the negative 9. We've got 2 more small numbers. This one here matches with 8.1 times 10 to the negative 6. And our last negative for our small number matches with 0.00081, and our last big number matches with that. So we've had a look at going from normal numbers into standard form, and from standard form back into normal numbers. We're going to have to use both of those skills now when we look at calculations involving standard form. We're going to look at 2 sets of calculations, one with adding and subtracting, and one with multiplying and dividing. Let's have a first look at adding and subtracting. There's 3 steps you're going to have to follow on this. First, convert your numbers back to normal numbers. We're then just going to perform the addition and subtraction as we would normally with any other numbers, and then we're going to convert back to standard form afterwards. So on your sheet, you've got a calculation, same thing I've got here on the board. 3.4 times 10 to the power 2, positive number, big number, add 7.05 times 10 to the 4. Have a go, follow those 3 steps, convert back to normal, do the calculation, and then back to standard form. Off you go. Let's see how you got on. So our first step was convert these numbers back to normal numbers. If we have a look here, our first 2 numbers, the first number is actually just 340, and our second number, 70500. So once you've converted those numbers into normal numbers, you just add them together. As soon as you've got your number added together, change it back to standard form. And what we're looking at is here, 7.084 times 10 to the power 4. Let me give you one more to try on your own. On your page, 1.23 times 10, this time to the negative 3, subtract 2 times 10 to the minus 4. Exactly the same process as our last one. Off you go. So once again, our first step, convert these numbers back to normal numbers. Converting them to normal numbers gives us these. Doing our subtraction gives us this value here, 0.00143. Converting it back to standard form, this number here between 1 and 10, multiplied by 10 to the negative 3. So remember those steps. When we're adding and subtracting, convert back to normal numbers, do the addition and subtraction, and then give your answer in standard form. In the exam, they'll generally say, work out this calculation, give your answer in standard form. So it's really important you convert back at the end. So multiplying and dividing is a little bit different. There's no converting back to normal numbers. In this case, we rearrange, and I'll explain what that means in a moment. We then deal with the parts separately. That means the numbers we're going to deal with first, and then the powers. And then we just check, is the answer still in standard form? It might need adjusting at the end, so that little bit at the end is really important. So let's go through an example together. On your sheet, you have this calculation, 5.6 multiplied by 10 to the power 3, multiplied by 2.4 times 10 to the power 4. What do I mean by rearrange? What I want you to do is to pop your numbers together. So we've got our first number here, 5.6, here. 2.34 here. So there are our numbers together. And at the end, we've got our powers. 10 to the power 3 multiplied by 10 to the power 4. Now it's straightforward. We're going to deal with these numbers and then our powers. You might be without a calculator doing this, so we need to make sure that everyone's okay at multiplying our decimals together. You might remember from decimal multiplication, we just treat them like normal numbers. So when we've got this here, 5.6 multiplied by 2.4, actually all we need to do is 56 multiplied by 24, and we've got 1,344. And then we need to put back in our decimal place. So if we look at what we started with, 5.6 has one decimal place and 2.4 another decimal place. So all together there, we've got 2 decimal points. So again, in our answer, we're going to have to change it to 13.44 as opposed to 1,344. So that's decimal multiplication. You need to make sure you're confident doing that. And then we look at our powers. Well, here, we've got 10 to the power 3 multiplied by 10 to the power 4. Now, if I said to you that was x to the power 3 multiplied by x to the power 4, you know from your rules of indices that you're going to add these powers together. So actually, we're looking at x to the power 7. Exactly the same. Our bases are the same, 10 and 10. So we have 10 to the power 3 multiplied by 10 to the power 4 is simply going to give us 10 to the power 7. So what we've got now is 13.44, which we just calculated, multiplied by 10 to the power 7. Looks like standard form, but check your answer is still in standard form. Let's have a look at this. 13.44 times 10 to the 7. Yeah, our first number there is bigger than 10. So we're going to have to change this number back to a number between 1 and 10. So what we're looking at then is 1.344 times 10 to the power 8. So really important, that last step, that you're checking that your number is in standard form. So I'm going to give you one now to try. Another multiplication together. 4.1 times 10 to the power 5 multiplied by 9.3 times 10 to the power 4. Exactly the same steps. Remember your decimal multiplication. Check whether your answer is in standard form at the end. I'll give you 1 minute and then we'll go through it together. So our first step, we need to rearrange. Let's get these numbers together, 4.1 and 9.3. Put those together and then we'll put our 10 to the power 5 multiplied by 10 to the power 4. Decimal multiplication, we've got here 4.1 times 9.3. Remember, you might have to do this without a calculator. Convert it to 41 times 93. We get our answer, put our decimal places back in, and we've got 38.13. Our rules of indices tell us that we have a 5 here and a 4 here. We are going to add them. So we have 10 to the power 9 multiplied by 38.13. Our number is not in standard form. The first number is not between 1 and 10. We're going to have to change it like we did last time to 3.813 times 10 to the power 10. Let's have a look at division. When we're dividing, we follow exactly the same method we have just done with multiplying. We rearrange, we deal with the parts separately, that's the numbers and the powers of 10, and then we check whether our answer is still in standard form. So here, it's sometimes easier to write this as 7 multiplied by 10 to the power 8 divided by 2 multiplied by 10 to the power 3 over each other. We can then see that we have 7 divided by 2, which we know is 3.5. Multiplied by 10, our rules of powers say that we're going to do 10 to the power 8 divided by 10 to the power 3. We actually subtract our powers, so we have 10 to the power 5. We check whether this is still in standard form. Our first number, 3.5, a number between 1 and 10, yes, multiplied by 10 to the power 5. Our answer is still in standard form. This is the correct answer. I'm going to give you one more to have a go on your own. 8 times 10 to the power 3 divided by 1.6 times 10. Off you go, 1 minute, and we'll go through it together. Looking at this question, we're going to start in exactly the same manner. First off, rearrange. We have our 8 times 10 to the 3 all over 1.6 times 10. You may have noticed that there is no power on the 10. If there was no power, it wouldn't be there. But there is actually a 1. It's a little bit like writing 1x. We don't normally do that. We just write x. We know it's 1. And in the same form here, we have 10, but it's actually to the power 1. I would advise you to write that in as soon as you spot it, because it's easy to forget. So I'm going to write it in here as well. Dealing with the numbers first, we have 8 divided by 1.6. 8 divided by 1.6 is actually 5. That means that 1.6 fits in to 8 5 times. Let's have a look at this together. If you add 1.6 and 1.6, you're going to have 3.2. It's like adding 16 and 16, 32. That's 2 lots. If I double that, I'm going to get 64, 6.4. That's another 2 lots. That's 4 times it fits in. Add another 1.6, and I'm going to come up to 8. So 1.6 fits into 8 exactly 5 times. Then dealing with our powers here, we have 10 to the power 3 divided by 10 to the power 1. Remember our rules of index laws? 3 subtract 1. So we actually end up with 10 to the power 2. So our final answer to this calculation is 5 times 10 to the power 2. We're now going to look together at an exam question where you're going to have to apply all the things that we've been covering so far around standard form in a calculation. I'm going to read through the question with you and then I'm going to give you some time to have a go. We've got 2 metal blocks, one of copper, one of nickel. The density of the copper block is here expressed in standard form, 8.9 times 10 to the 3. We then have the density of the nickel block, which is 8.8 times 10 to the power 3. Both of these densities are expressed as kilograms per cubed metre. That's what our metre cubed there means. If we go back to that first step, it says that the 2 metal blocks have a volume of 2.5 metres cubed. That's going to be important in a moment. So our question asks us to work out the difference in the masses of the 2 blocks. and it wants the answer in standard form. 3 marks, 3 minutes, off you go. So what you're actually being asked to do on this question is just a simple subtraction. We have our first value for the density of copper, 8.9 times 10 to the power 3. Subtract 8.8 times 10 to the power 3. We've got subtractions here. Remember our first step, converting to normal numbers. If we convert those two numbers, we have 8,900, subtract 8,800. So we're left with just 100. So we have the answer of 100. But what we need to do then is multiply that by 2.5. Let's look quick back at the question. These two metal blocks each have a volume of 2.5 meter cubed, and the density is expressed as kilograms per meter cubed. So we must make sure that we multiply our answer by 2.5. Multiplying 100 by 2.5 gives us 250. Our last step, again, look back at the question, give your answer in standard form. So let's change this 250 into standard form. A number between 1 and 10, our only option is 2.5, multiplied by 10 to the power 2. Positive 2. Let's have a quick look. Decimal point here, 1, 2 places, to the power 2. Another problem. How long would it take a spaceship travelling at an average speed of 2.6 times 10 to the power 3 kilometres per hour to reach Mars, which is 8.32 times 10 to the 7 kilometres away? Within this question, it doesn't tell you which operation you need to use with these numbers. I'm going to give you 3 minutes to have a think about it, and then we'll go through it together. Off you go. So the first thing you need to think about in this question before you launch into it is we've got an extra dimension here. We've got standard form. We're also now dealing with the concept of speed. Now you need to be able to know that actually speed equals distance divided by time. We've got the speed and we've got the distance. What you're looking for is the time. How long would it take? So if we rearrange this, we've actually got time equals distance divided by speed. Immediately you've got the operation there. Distance divided by speed. We have the distance, we have the speed. We're going to be doing a division. So all you then need to do is substitute in your values for distance and speed. We have the distance divided by the speed here. 2.6 times 10 to the power 3. Working that out in the same way we've been doing, working our numbers out first and then our powers, gives us an answer of 3.2 times 10 to the power 4. Also include your hours there because we're looking at time, and our speed is expressed in hours, kilometres per hour. Our answer here is going to be in hours as well. So what we're going to look at now are some percentages. We're going to start with some simple percentage increases. The first question I've got for you is calculating the cost of a lamp. This antique lamp was bought 20 years ago for the cost of £50, and it's increased in value by 24%. I want to know what the price of the lamp is now. You can use a calculator, you can do it without a calculator, any method you want. I'm going to give you 2 minutes. What is the new price of the lamp? Off you go. So with all percentage questions, there's a number of different methods that you can use. I'm going to explain 2 to you. The first one is without a calculator. So we need to find 24%, and then we're going to increase. We're going to add it to the original value. So our first step, we know 100% of the value, £50. It's what it started at. 10%, divide through by 10, £5. And 1% is 50p, 0.5. Now, from that combination of 10% and 1%, you can work out any percentage that you want. 72. I need 7 lots of 10, 2 lots of 2. 33. 3 lots of 10, 3 lots of 1. So that's a really, really good base to be able to work out any percentage that you're asked. In this case, we're asked for 24%. So I need 2 lots of these, 2 lots of 10%, make my 20%, and I need 4 lots of my 1%. So if I need 2 lots of 10%, that's going to be 2 lots of £5, which is £10. And I need 4 lots of 1% to give me my 4%, which is going to be £2. 20%, £10. 4%, £2. Add those together and you've got 24%, which is £12. So actually, going back to this question, 24% of £50 is £12. And it's increased, it's gone up. So we've got £12 plus your £50 is going to give us the new value for the lamp at £62. All of that straightforward without a calculator. As you can see here, my box is smaller. There's a quicker method which you can use a calculator for. This is using multipliers. So what we actually want is 124% because we're increasing it by 24%. And our multiplier for that is 1.24. So simply on your calculator, you would type in 1.24 multiplied by 50, and you should come out with the same answer of £62. So both methods work. If you know the one on the left, it's going to get you through the non-calculator paper as well as the calculator paper. Method on the right is a good method to know with these multipliers, which we'll be coming to later. Let's have another look at a different question. This time we've got a jacket costing £86, but it requires VAT at 17.5% to be added. So a slightly different percentage here, 17.5. Same, on my left I've got a non-calculator method, on the right I've got a calculator method. I'm going to give you 2 minutes, you go, have a go for yourself, and then we'll go through together. Off you go. We're going to start this question in exactly the same way. We're going to look at 100%. We know 100% is the whole amount of the jacket, £86. We're going to find 10%, as we did in the last example, which is dividing through by 10, which gives us £8.60. Then we're going to do something slightly differently. Instead of going to 1%, we're going to look at 5%. This is going to make it easier to find 17.5. So 5% is half of 10%. So we divide our value for 10%, £8.60, by 2, which is £4.30. Half the 8, 4, half the 60p, 30p. Then we're going to do exactly the same process to get 2.5%. 2.5 is half of 5. So once again, we're going to halve our value for 5%, which is £2.15. Now, we have 10%, 5% and 2.5%. Add those 3 up, 17.5%. So what we're going to do now is just add our values up here to get 17.5%. So over here, if we have £8.60, £4.30 and £2.15, I'm going to have 5 here, add those up, 10, carry my 1, 8, 9, 10, 11, 12, 13, 14, 15. So 17.5% is actually equal to £15.05. Going back to the question, we need the jacket costing £86 and then we need to add the VAT to it. So we have £86, I like to add my 2 zeros in here, and then £15.05. Add those up and we have 8, 9, 10, £101.05. Again, all without a calculator. Alternatively, we can use a calculator. If we want to use a calculator, we can use our multiplier like we did before. We've got 100%, add 17.5%, is actually 117.5%. So our multiplier is 1.24. 0.175 multiplied by 86 comes out on the calculator exactly the same answer, £101.5. So the next question I've got for you is going to combine both of those skills together. It's a question that involves VAT. It says that in January 2010, the rate of VAT was increased from 15% to 17.5%. So we've got a games console that's worth £199, add VAT. And what the question is asking you to do is how much more expensive was it to buy a games console in January 2010 than in December 2009. So you're going to have to work out the differences in the two prices with the different percentages. I'm going to give you 4 minutes for this question. Off you go. So one of these questions is probably, in the exam, going to have this little mark next to it. It's the asterisk mark. And this asterisk mark means that there is a mark available for your quality of written communication, which actually means how have you laid out your working and have you put down your working out clearly as well as your conclusion. So we're going to have a look at how I've decided to lay this out. On my left-hand side here, I've decided to work out the value here of the games console, £199, add 15%. So that actually was the value of the game console in December 2009. Might be good to put a label there so the examiner knows exactly what you're working out. 199 multiplied by 1.15 gives us our value there. On this side, as a comparison, I've worked out the value at 17.5%, which is our multiplier of 1.175. And we have a new price. And again, this is for January 2010. So my question asks, how much more expensive? Once we've got our two values for December 2009 and January 2010, we're going to have to take them away from each other to find the difference. So we have the value here for January 2010, subtract the value from 2009. And we have a difference of 4.975. What we then need is this last bit, and this bit's really important. This is explaining what we've worked out. Now, 4.975 is not an amount of money. So what we normally do is round that value there. So 75 rounds up to 8. So we have a value which is actually money, which is £4.98. And then key, more expensive in January 2010. That sentence there is you communicating to the examiner that you realise that in January 2010 it was this much more expensive than in December 2009. And that is why there's going to be a star here and an extra point available for this sentence at the end, which is your conclusion. What we're going to look at now is percentage decrease. Works in a very similar way to percentage increase. We're going to start with some simple questions. An MP3 player originally costing £75 is reduced by 32% in a sale. What is the sale price? 2 minutes, off you go. So following a similar pattern that we looked at for the increase, on the left-hand side here, I've got the working out without a calculator. First off, we're going to look at 100%. We know that 100% is £75. It's the original price. It's all of it. 10%, £7.50, 7.5, and 1%, 0.75, 75 pence. Again, once you've got that 10% and 1%, you can work out any percentage. In this case, we need 32. So I want 3 of those, and I want 2 of those. So that's 3 lots of 10 to make my 30, and 2 lots of 1 to make my 2, the 32. Add those up, and I'm going to get £24. Now, this time it's a decrease. So instead of adding this to my original price of £75, I'm going to have to subtract it. So my value at the end is going to be less than the original price. It's a percentage decrease. So £75, take away £24, leaves us with £51. Let's now look at the method with a calculator using our multiplier. So we've got 100% as our original, and this time we're taking away 32%. It's going down by 32%. So actually, all we're looking at is 68%. So we need to find 68% of our 75. Using a multiplier, that's going to give us 0.68. 0.68 times by 75 comes out the same answer, £51. Let's go back there. Here, we are doing 100% to subtract 32%. And that's why we're left here with 68%. Our multiplier for 68% is 0.68. So same answer we get here again, £51. 2 questions for you to try. Choose whichever method you want, either using the non-calculator method or the calculator method, or both to practice. 2 minutes, off you go. So the first one that you're asked to work out is a car bought 5 years ago for £13,000, and it's decreased in value by 40%. So it's going down by 40%, so you're actually only looking at 60%. Our multiplier for 60%, 0.6, multiplied by the original value, down 7,800. Our second example is a bicycle costing £350. Again, it's been reduced, this time by 15%. So 100%, take away 15%, it's going to leave you with 85%. Our multiplier for 85, 0.85, multiplied by our original price here, 350, gives us £297.50. So what we've gone through so far is simple percentage changes, both increases and decreases. You need to be confident using your calculator and multipliers and being able to do it without a calculator. What I've got an activity for you to do now is practicing these multipliers. On the left-hand side in yellow, you have 7 descriptions of percentage increases and decreases. On the right-hand side, you have some blue diamonds with multipliers in. You need to match these multipliers with the descriptions on the left-hand side. 3 minutes, off you go. So let's have a look at these together. Our first one says increase by 50%. If we're increasing something, we've got 100%, and we're actually adding another 50%. So actually we've got 150%. That gives us a multiplier of 1.5. So this one matches in here. Let's have a look at the decrease. Decrease by 80%. We start with 100%. We're decreasing, so we're subtracting our 20%. And we know that that leaves us with 80%. So a percentage of 80 is a multiplier of 0.8. So this one here matches up. Our next one, increase by 15%. 100 plus 15 is 115. And our multiplier is 1.15 here. Decrease by 5%, 100%. Take away 5%, leaves us with 95%. Our multiplier is 0.95. The next one says increase by 20. 100% plus 20%, 120%, 1.2. Our last two are decreases. We can see the last two remaining here of multipliers are actually less than 1. So we know that it's going to be right because our decreases are always less than 100%, which is less than 1 in the multiplier. Our first one is decreased by 34, which is 0.66, And our last one is decreased by 95%, which is 0.05. So these multipliers are really, really helpful because when we look at compound and repeated percentage change, this is going to make it a lot easier for you. On our next slide, we have compound percentages. This is when two percentages are put together. Let's look at this example together. A jacket is reduced by 20%, so going down by 20%. 2 weeks later, the shop reduces the price again by a further 10%. My question to you is, what is the total percentage discount? Have 30 seconds to think about that. So, the total percentage discount, it is not 30%, which is commonly thought. If you go down by 20%, down by another 10%, well, that's 30% altogether. Let's have a look at why that's not the case by using our knowledge of multipliers. Let's look at this. First off, if we want to decrease by 20%, remember what we just did. 100%, take away our 20% leaves us with 80%. So our multiplier is 0.8. Our second percentage decrease is 10%. 100%, take away 10%, leaves us with 90%. A reduction of 90% is equivalent of a multiplier of 0.9. So our first multiplier is 0.8, our second multiplier is 0.9. We don't know what the original price of the jacket was, but let's just write out the original price, whatever that may be, times by 0.8, the first multiplier, times by 0.9, the second multiplier. Multiply our 0.8 and our 0.9 together is 0.72. So actually, we're looking at original price multiplied by 0.72. Well, 0.72 is equivalent to a discount of 28%, not 30%. So here, what we're looking at is compound. So when one percentage and then it's affected by another percentage, we don't just necessarily add those percentages together. Let's have another look at another example together. In this example, Jenna invests some shares. After 1 week, the value goes up by 10%, and the following week they go down by 10%. So has she made a loss, a gain, or is she back to the same at the beginning? Show you're working out, think about multipliers. 2 minutes, off you go. So we've got two multipliers here. Our first multiplier is going up by 10%. That's 100 plus 10% is our multiplier of 1.1. Our second multiplier is going down by 10%. So that's going to give us 0.9. Let's just remember, going up is going to give us 110%, which is a multiplier of 1.1. And going down is going to give us 90%, which is 0.9. If we multiply those two numbers together, we've got 0.99. So it's not going to be the same. If we have our original price of our shares multiplied by 0.09, there's going to be a loss of 1%. So again, with these compound interests, you need to do the multipliers to see the effect. Let's have a look at this together. We're going to look at compound interest. Jack puts £500 into a savings account with an annual compound interest rate of 5%. Straight away, 5% interest rate is an increase, so we know our multiplier is going to be 1.05. That's 100% plus 5%. The question is, how much will he have in the account at the end of 4 years if he doesn't add or withdraw any money? There's two ways you can do this. First off, as a single calculation. So £500 is the original amount, multiplied by our multiplier, 1.05. 1, 2, 3, 4 times. That's because we're doing it for 4 years. So this is fine to type into your calculator, provided that this number of years is not too many. If this changes to 20 years or 30 years, for example, you would have to type in 30 times 1.05, which is just not practical. So what we use instead is index notation. We have our original amount, £500, multiplied by 1.05 to the power 4, 4 representing the number of years. If you're using index notation, it's really important that you know where the button is on your calculator. It's normally at the top section, above the numbers. On my calculator, the button looks like this. So what I would type in is 1.05, this button, and then 4. That means to the power 4. On other calculators, it might be y to the x, meaning the x bit here is your number of years being 4. So it's really important you know your own calculator. And again, the number comes out the same. So this here, using index notation, is the best way. Let's take this a next step further. How much would Jack have after 10 years? So instead of 4 years now, 10 years. And the second question I want you to answer is how long would it take for the number to double? 3 minutes, off you go. So once again here, we're going to use our index notation. We're going to have our original amount, 500, multiplied by our multiplier, we're increasing by 5%, to the power 10, 10 representing the number of years. And this is your answer, rounded to the nearest penny. We're talking about money. The next question, how long would it take for the money to double? Now we started off with £500. So if we're looking for the money to double, we need £1,000. To work this out, you're going to use trial and improvement. So our first step is to choose a number. If we've got here 10 years, looking back, that takes us to £814 you've worked out. If you go up 11 years, 12 years, 13 years, you can see that these two here, the 1.05 to the power 14 and 1.05 to the power 15, one is just below 1,000 and one is just above 1,000. So actually, it's going to take 15 years for your number to double. If you look at these two here, this one is going to be your answer because actually after 14 years you're still under 1,000. So you've got to go over the 1,000 mark, which means then your answer is 15 years for your money to double. Again, using trial and improvement. Let's have another look at one of these questions from the top. Powers are used in solving problems involving repeated percentage increase and decrease, as we've just seen. The population of a village increases by 2% each year. Firstly, if the current population is 2,345, what will it be in 5 years? And what will the population be after 10 years? 4 minutes, go. Our first question asks us about the population after 5 years. Our percentage increase is 2%. To increase the population by 2%, we need to multiply it by 1.02. The calculation we're going to carry out is the original population, which we see here, 2345, multiplied by the multiplier to the power 5. 5 is the number of years. Again, to the nearest whole number, rounding, that's going to give us 2,589. Our second question is after 10 years. All that changes, you can see here, is our power. We've now got a power to 10. Again, we still round to the nearest whole number because we're talking about population, people. So we have 2,859. The next question I want you to have a look at is about a depreciation. It says the value of a new car depreciates at a rate of 15% per year. A car costs £24,000 in 2005. This word depreciate exactly the same as decrease. It's going down, okay? 15%, we start with 100%, we go down. So we have 100%, subtract 15, leaves us with 85%. Think back to those multipliers. A percentage of 85 has a multiplier of 0.85. The next part you're asked, how much will the car be worth in 2013? It doesn't tell us the number of years, but we can work that out. We've got the value of the car in 2005. So between 2005 and 2013, we have 8 years. I want you to apply what we've just been looking at with multipliers and powers to see if you can find the new value of the car if it decreases by 15% for 8 years. 2 minutes, go. Looking at this question, our first step is to realise our multiplier. As we've said, it's 0.85. Our second step, as we've looked at, is that there are 8 years between 2005 and 2013. Putting that information, given we know the original cost of the car, which is $24,000, multiplied by our multiplier, 0.85, to the power 8 years, gives us a new value of 6,540. Again, rounded to the nearest pound. That's a reduction, as makes sense, that the car is depreciating, which is going down 15% each year. What we're going to look at now together is an exam question. Again, it's one of these ones with the asterisks, which means quality of written communication. It is very important how you lay your working out and that you show your examiner your conclusion. We're going to read through the question first together. Henry wants to invest £4,000 for 2 years. Original value, 400, 2 years. He can choose between 2 different banks. We've got Bank A on the left, Bank B on the right. Let's have a look at what Bank A is offering. 3% per annum compound interest. Bank B, 3.2% higher per annum simple interest. Each year's interest is paid by cheque. We'll have a look at those in a moment. Henry wants to earn as much interest on his investment as possible, so he wants the biggest amount of money at the end. Which bank should he choose? Show your working. Let's go back a step. Per annum. That actually means per year, okay? So simply per year, which is just as we've seen in before when we had 8 years in the last example. Our bank here, A, has compound interest. Bank B is just simple interest. That's like what we were doing right at the beginning. And it says here, each year's interest is paid by cheque. It's irrelevant. It doesn't matter. Henry wants the most amount of money. You'll often find that in some exam questions, they give you additional information which is not going to affect your answer. So simply ignore that part. It's worth 5 marks. I'm going to give you 5 minutes, compare the banks, see which is the best bank for Henry to put his money in. Off you go. Let's have a look at this together. So, Bank A, compound interest, original amount, £4,000, multiplied by our multiplier, 1.03, that's 100% plus 3%, to the power 2. Just for 2 years he's investing, and we get our value here. For Bank B, it's not compound interest, so there is no powers involved here. We just simply find the interest for the year, so our original amount, multiply by 0.032, that extra bit there because it's 3.2%, gives us £128. So each year in Bank B, you just get £128. So the first year £128, the second year £128, etc. There is no compound there. So if we get £128 per year, Henry's going to get £256 for a 2-year period. We add that to the original amount that he put in, and he's going to get out at the end of the 2 years this value here, 4,256. But the question wants to know which bank. You've done all the working out now. You need to make the conclusion. So looking at our two values, Bank B has a higher value at the end. So again, on your exam, very clearly in a sentence, Bank B is the better choice, as Henry will receive £12.40 more interest. Really clear and concise conclusion. Show you're working out for both banks, write your conclusion. You have now completed the number section on standard form and percentage change. You now need to pause the video to take the number assessment. Good luck. Section 2 is on data. We've got two topics. One is cumulative frequency and box plots, and our second topic of B grade is tree diagrams. Cumulative frequency. I've got two lists of numbers on your sheet, and a cumulative frequency is like a running total. So let's have a look. Our first number is 3. So we just write 3 down next to it. Our next number is 6. We add 6 to the 3, and we get 9. Our next number is 10. 9 plus 10, 19. 19 add 4, 23. 23 add 2, 25. 25 plus 12, 37. 37 add 5, 42. And 42 add 8 is 50. This column here that we've just created is the cumulative frequency. On the left-hand side, we have the frequency. On the right-hand side, in the orange writing, is the cumulative frequency. It's the running total. The number here at the bottom, which comes as 50, will be the same number if you add all of those up to check. I'm going to give you 1 minute now for you to do the cumulative frequency to the second column of numbers. Off you go. So just as we did before, the first number is 2, stays as 2. We then add our second number, 4, which makes 6. 6 add our 1, makes 7. 7 add our 14, makes 21. 21 add our 6, makes 27. Again, I'm going across and down. The arrows might help if you want to put those in as well. 27 add 8 gives you 35. 35 plus 3 gives you 38, and 38 add 12 gives you 50. Again, cumulative frequency is simply adding up the numbers gradually as you go down the column. Now, what you're going to see in the exam is this presented in a table. Let's have a look at this. Here are the results of 100 people holding their breath. On the left-hand side here, we've got some groups. T stands for time, 30 to 35, 35 to 40, 45 to 50. There's inequality signs in between, which is less than or equal to. Don't worry about those, we've just got groups here. Our second column is the frequency, just like we had on the last slide. Then we have another column which says, what is the time between 0 and 35, 0 and 40, 0 and 45? This is what you're going to create the cumulative frequency. So, our first frequency is 9. Put that in. Add your 12 to 9. 9 plus 12 is 21. 21 add 24 is 45. 45 plus your 28. 40 plus 20 is 60. 8 plus 5 is 13. So we have 73. 73 adds 16. Well, the 70 plus my 10 is 80. And my 6 plus my 3 is 9. And then I've got 11. Add to my 89 makes 100. Check back in the question. Here are the results of 100 people. I've also got 100 here. You need to do that. If that number doesn't match what it says in the question, you've just made a simple arithmetic mistake above. go back, try again. Now it could be presented like this, where you've got your groups, your frequency, another set of groups, and then your cumulative frequency. Just so you're aware, it could also be in two separate tables. So I've just popped that slide up there for you to see that it might be one table above and then another table below that you need to fill in. Exactly the same thing. So in all the cumulative frequency questions, if you need to draw the graph, you're going to have to create the cumulative frequency by adding up the totals. So cumulative frequency is actually a graph. It's a particular graph that is an S-shaped graph, and it has a really smooth curve on. So always an S shape, and it's going to have a curve. Now, let's have a look at the graph. Always in the exam, you're never expected to draw the axes and label them. They're always drawn for you. So let's see. We've got on our x-axis here, time in seconds. Now that matches with this column here that we looked at earlier about holding your breath. On our y-axis, we have the cumulative frequency, which you would have found out in part A, and we've got it copied here for us, 9, 21, 45, 73, 89 and 100. Now what you're going to plot is the cumulative frequency, as it says there on the y-axis, against these numbers here, okay, which is the upper class boundary. But it's the second set of numbers. It's always going to be these ones here on the right. So how are we going to plot? Nice big cross. Okay, it makes it really, really clear. If you do a little circle, sometimes it can be missed. You need to remember that your exam papers are actually scanned in and put on computer screens, so you've got to be really, really clear. Also, obviously, we're doing graph work, a pencil. You need to be able to make sure that you can rub it out if you put your point in the wrong point. Okay, so your first one, we've got 35 on our time. I go along 35 on my x-axis, and I go up to 9. So really carefully plotting my point there as a cross. My next one is 40, and I go up to 21. Okay, 4 more points for you to plot. Off you go, and we'll go and have a look at the graph together in a moment. 1 minute, off you go. On the screen now, you will see the completed cumulative frequency graph. It's got the 6 points plotted. It goes through the origin. It starts at the origin. That's not a point that was to plot. You need to add that in. And you can see the nice smooth curve, which looks like an S. It's a sort of stretched S, okay? And that's typical of a cumulative frequency graph. So if you're not getting that shape, you've either made a mistake on the plotting or a mistake on the cumulative frequency. Once you've plotted the cumulative frequency graph, we can then work out further things from the graph. The first thing we're going to look at is the median. Now, the median is the middle point on the graph. Now, we can use this graph to estimate the median of this data. We've got 100 people, so the halfway person is going to be the 50th person. So our first step is always to take the total, which in this case is 100, divide it by 2 to find the value we are going to be looking for on the cumulative frequency. It's 50, it's the 50th person, it's the halfway, which you can see here on the graph. I want you all now to go to 50 on your graph. Just as you can see here, get your ruler, draw a line across to the orange line, the cumulative frequency graph. As soon as you hit that line, drop your ruler down and read off the value on the x-axis for the time. And on this case, it should come out at 46 seconds. See if you get that as well. The next thing you may be asked to work out is the interquartile range. And we can use our graph to do this as well. We need to find the lower quartile and the upper quartile. The lower quartile is the time of the 25th person, okay? Halfway between the medium here and the bottom at 0, which is going to be 25. And this here is your lower quartile. Exactly the same as the medium. Use your ruler, draw a line across, hit the cumulative frequency graph, down, read the value off, 41 seconds. The upper quartile is halfway between the total, 100, and our medium, 75, just here. Ruler across, ruler down, read off the value, and to be really precise, it comes out at 50.5. You might get 51 or 50, depending on how you've drawn your graph slightly, but there will be a margin where you can be in for the answers. Once you have your upper quartile and your lower quartile, you can work out the interquartile range by subtracting your lower quartile, 41, from your upper quartile, 50.5, which gives you the value of 9.5 seconds. Now, all of these things you've just worked out, the median, the upper quartile and the lower quartile, means that you can then draw a box plot, which is a further graph derived from a cumulative frequency graph. Once you've calculated the median, the interquartile range by using the upper quartile and the lower quartile, it makes it really easy to draw a further graph called a box plot, which we'll look at in a moment. First off, a quick exam question for you. We've got a cumulative frequency graph has been drawn. You can see on your sheet here, this is a graph about 120 houses. First off, I want you to find an estimate for the number of houses with prices less than 130,000, and I want you to work out the interquartile range. There are 120 houses this time, not 100. 3 minutes, off you go. Part A is looking for you to find the number of houses with a price less than 130,000. If you go to the x-axis, where it says prices of houses, you need to find the value for 130,000. Looking at what's labelled on your axes, you can see here 120,000 and here 140,000. So 130, even though it's not labelled, is going to be halfway between that. At that point, you need to get your ruler, draw a line straight up to the line, and then you're going to join a line across. So your line is going to come along here. Again, use your ruler. We can then see the cumulative frequency, which comes out on my graph here at 68. Again, you might be slightly higher, slightly lower. 68. Now, it says for the number of houses that are less than 130,000. So all of these houses here are less than 130,000. So our answer is directly 68. However, that question could have been asked for the number of houses that are more than 130,000. And at which point then we would have to do 120, the total, subtract 68 to find the number of houses that are more than. So be aware of that. Part B asks you to find the interquartile range. Now in this question we have 120 houses. So halfway is going to be 60. Let's label that up there, 60. Halfway between 0 and 60 is going to be 30, which is your lower quartile. And halfway between 60 and 120 is going to be 90. That's your upper quartile. So once again, at 30, a line across and down. At 90, a line across and down, which should look like this. So your two lines across, do them really clearly with a ruler, and your two lines coming down. Extend them if you wish to. See, my line for 30 has gone too far. So just pull that back to there so it touches the line only. And then a further line to come down. So really try and be accurate when you're doing these. So we have our upper quartile reading off the x-axis as 145,000, 145,000, and our lower quartile just down here at 95,000. And to find the range, as we remember, we're taking away the lower quartile from the upper quartile. So we do a subtraction, 0, 0, 0, 0. 4 take away 9 doesn't go, so 14 take away 9 is 5. So the difference between the upper quartile and the lower quartile is £50,000. Again, you might have a slightly higher or a slightly lower answer. That's not a problem. Let's now have a look at box plots. Box plots can be called something else, also box and whisker diagrams, you may know from the shape of them. And they're used to illustrate the spread of the data. How spread out is the data? And they use 5 particular values, which are labelled here. The minimum, the lower quartile, the medium, the upper quartile, and the maximum value. So those 3 things we worked out earlier together, and the maximum and minimum value tell you the extremities. How does this look? Well, what you've got here is a blank grid. And what I want you to fill in is, with me, the box plot. So our lowest value is at 30. So along our x-axis we go to 30 and we just draw a little line. Our upper value, our maximum value, is 60. 60 along the x-axis, and again we're drawing a little line. We then have 3 further values, and that's where the box is. So our 2 extremities, the maximum value and the minimum value, are the whiskers. Then we've got our box in the middle. So our lower quartile at 41, we draw a line there, but I want you to make that line a bit longer than our other 2. Same thing at our medium, 46, and again at 50.5. So we've got 5 vertical lines. The 2 at the end are short, the 3 in the middle are longer. We then connect the 3 in the middle to make a box. So we have a rectangular box in the middle. This then extends out here and here. That's a box plot, 5 particular values, and you're often asked to complete one of those after doing a cumulative frequency graph. If I can just show you here now, for your reference, for any box plot, minimum, lower quartile, medium, upper quartile, maximum. Another exam question for you to try. The weight in kilograms of 50 people in a club was recorded. The cumulative frequency diagram shows results. It's done for you. Again, it's a smooth S-shaped curve. It starts down here at 0. Weight along the x-axis, cumulative frequency on the y. Using that graph, I want you to find an estimate for the median, the interquartile range. Then I want you to write down the percentage of weights represented by the interquartile range. And then we're going to look at a box plot. So all of those things are going to give you 5 minutes to do it, and then we'll go through them together. Off you go. So looking at this graph, our first thing we need to do is to find the upper quartile, the lower quartile, and the median. How many people have we got all together? This time we've only got 50. So what's half of 50? 25. That's where our medium is going to go. Once again, halfway between 0 and 25 is 12.5. Here we've got 10, they're going up in 2s. That's 12, that's 12.5. Halfway between our medium and our total of 50 is again 37.5. That's 30, 2, 4, 6, halfway 7.5 is approximately just there. So that's your upper, and here is your lower. You then need to draw your lines across and down. Having used your ruler to draw a cross from the medium, the upper quartile and the lower quartile, you can then see the blue lines going across and then going down. Really clearly, we then have the values of 62, 66 and 72. Our medium equals 66. Again, a little bit above, a little bit lower is okay. And our interquartile range is going to be our upper quartile, 72, subtract our lower quartile, 62, which gives us a value of 10. Part B asks you to write the percentage of weights represented by the interquartile range. Whatever the context is, the interquartile range represents 50% of the data. The upper quartile is at the 75th percentage point, and the lower quartile is at the 25th percentage point. Subtract those two, in between is 50%. So every time the interquartile range represents 50% of the data. Below is 25%, above is 25%. The next point asks for the box plot. There is no scale drawn here, so you need to do this. Looking back at our graph, we have our three values for our upper, medium and lower quartile. We know that it goes from 62, 66 and 72. And we can see our lowest value is actually given in the question. It says that the lowest weight recorded was 50 kilograms and the heaviest was 90. So we need a scale that goes from 50 to 90. If we count along here, we start here and we make 10 for each square. We start here at 50, this is 60, 70, 80 and 90. You'll always be given enough paper to make a nice scale. So at 50 here we have our lowest value, that's just a small vertical line. At 90 we have the largest, which is just there. We then have our three values for the upper quartile, lower quartile and medium. 62, which is here. Our upper quartile, which is 72, which is here. And our medium, which is 66, here. And then we connect these to make a plot. Once again, in the exam, you'll be using a ruler to make these lines nice and straight, and you're presenting your work well. We've looked at questions that have cumulative frequency followed by box plots. However, you can also get questions with box plots on their own, and this requires you to be able to interpret what the box plot is telling you. If we look at this question here, it's about gender differences in income for a company. We've got on the left here our females, we've got our highest, our lowest value. We then have our box in the middle with the upper, lower and medium, and the same thing for the men. Now we've got a comment. It says the interquartile range is the same for male and female. This shows there is no difference in the incomes for males and females. Do you think this interpretation is correct? I want to have a think about that for a minute, jot down any notes and we'll go through it together. Despite the interquartile range being identical between the males and the females, if we look at these box plots, we can see differences. Let's look at the median. The median for the females is here and for the males here. The female median is lower than the male. So on average, females earn less than males. We can also see differences at this end, here and here. These are the maximum incomes. 70 for females, but over 80 for males. So again, a difference that we can comment on. So let's have another look at some box plots. This time we have 3 box plots. You may well be asked to make comments about these in the exam. So you need to look at differences between them to compare. We can look at the maximum values. So Dunning has the highest maximum value. Looking at the mediums, Hampton has the highest median. You could calculate the interquartile range by subtracting the lower quartile from the upper quartile and seeing which one has the biggest spread. There are lots of comments you can make about the different box plots. You need to ensure that you look at the number of marks and then say the number of different things about the box plots. We're now going to complete an exam question together. You will notice that this exam question also has an asterisk next to it. So once again, the quality of your written communication is being assessed. This question starts with a cumulative frequency. You're then going to draw a box plot and you're then going to compare. 7 marks are available. You're going to have 7 minutes to do this. Off you go. Let's have a look at this question together. We have 80 students who are taking a maths exam. The maths exam had 2 papers, just like you have. The cumulative frequency table gives information about the marks scored on paper 1, the non-calculator paper. The cumulative frequency is given for you. So the first thing you need to do is draw the cumulative frequency graph on the table. So let's have a look at the graph. I've got the points plotted here. So with my pencil, I'm going to draw a nice smooth curve through the points, starting here or at the other end and through. You can see here I haven't quite gone through the zeros, so I'm going to rub that out and then go back on the last bit. Again, that's no problem for you to do in the exam, to try and get it as smooth as possible. Once that graph has been drawn, you're then given some further information. The lowest mark was 9 and the highest mark was 52. And they want you to draw a box plot. We can't do a box plot without knowing the medium and interquartile ranges. So going back to our graph, we know that there are 80 students altogether. Half of our 80 is going to give our medium, so that's 40. So 40 along here, we're going to have to draw our line across again. Half of that is 20, so that's our lower. And then again, 60 is our upper. So with our rulers, I'm going to get my tool on here to draw a straight line. So my upper, 60 goes across to the line, 40 goes across to the cumulative frequency line, and 20. Once you've drawn all your lines across, you're then going to do your lines down, your vertical lines down to the x-axis. So we have a line here, a line here, just under 30, and our last line here at 20. So we now have our upper being equal to 37 on my one, our median, which is our middle value, equaling to 29, and our lower quartile, which reads off from my graph at 19. And those 3 pieces of information we're going to need for our box plot. So we've got 19 for our lower, 29 for our medium, and 37 for our upper. In our question, we're also given that 9 is the lowest and 52 is the highest value. We now need to draw a box plot. So if you just look down onto your sheet, you've got 2 spaces here for your box plot. The second one is drawn for you. It might be a bit faint, so I'll just go over this one so you can see exactly where it is. My lines here, and this is for paper 2. So paper 1, our lowest mark was 9, so line at 9, remember that's just the little line because it's the minimum value. Line at 52, that's the biggest value. Then we have our lower quartile, which is 19. Now if you got slightly different values, say you got 20 for your lower quartile, you should be plotting 20, as I've got 19. Then 29, so that's again there. And the last one, our upper quartile, being 37. That's 40, let's go 3 backwards, and it's there. And then join up, again a ruler, line, line. Then we've got 2 box plots. And our last question asks us to compare these. So you can see here, if we go back to the question, compare the marks scored by students on paper 1 with the marks scored on paper 2. So we've got our 2 box plots that we're looking at together. Just as we've done before, we're going to spot differences. So paper 2, maximum mark is higher than on paper 1. You can see these 2 here. Change colour. Here are maximum marks. So we can say the maximum mark on paper 2 is 55. The maximum mark on paper 1 is 52, therefore higher. We could look at the medium, for example. The medium on paper 2 is here, which is 32. The medium on paper 1 we had down as 29. Again, yours might be slightly different, 3 less. Here, paper 2 has a lower mark. The lowest mark on paper 2, a student must have scored 6 marks. However, in paper 1, it's as low as 9. any of those things, there's a whole list of things that you could list. Again, look how many marks are available, that's how many things you need to list. And normally there'll be dotted lines saying 1 and 2. So cumulative frequency, as I said at the beginning, we've got the graphs and the interpretations and box plots. All of those things could appear in a question together or just part of it. We're now going to move on to tree diagrams. Our next topic is tree diagrams, and this is related to probability. Let's say you have 15 playing cards. 6 of the cards are red and the rest are black. Immediately, I want to write down red equals 6. And I can know that if there's 15 altogether and 6 are red, then 9 are going to have to be black. Now I don't write out red, black, I'm just using notations. R equals 6, B equals 9 for the red and the black. My question says, what is the probability of choosing a card at random from the set that it's red? So how many are red? 6. What's my total? 15. So very simply, our probability for red is going to be 6 over 15, which if you want to express as a decimal is 0.4. You decide to pick a card at random from the pack. So you have 15 cards, you pick one up, you look at it, you replace it, and then you pick another card up. You look at it, record what it is. The replace bit is key, and this is a word that you will see or not see, and it might say does not replace in the question. If you pick 2 red cards, so I've got my 15 cards, 6 of them are red, I pick a red one, look at it, put it back in, pick another red one, you need to stay in and do your homework. That's the outcome. If you don't pick 2 red cards, you're going to go to a party. And we want to know what are the chances of that happening. So we do a tree diagram. This here is a representation of a tree diagram. You can see we start here in the corner and we have branches. Often tree diagrams at GCSE level have 2 sets. So on our left hand side it's the first time we pick out, and on the right is the second time we pick a card. There's only 2 options, red or black cards. Here in the red, we worked out the probability of picking a red was 0.4, or as a fraction, 6 over 15. So I'm going to write in 0.4. If the probability of getting a red is 0.4, the probability of getting a black has to be 0.6, because our probabilities add up to 1. Now I pick the card up, I look at it, I put it back. It's been replaced, so there are still 15 cards. So if I go to pick another one, the probability is going to be identical. Nothing has changed. So again, I write in here 0.4, if you can do this at the same time, 0.6, 0.4, 0.6. Often 2 marks available for just filling in that information. Now, the information in the question said that if you get 2 reds, red, put it back in, pick another red, put it back in, you're going to stay in and do your homework. If not, you go to this party. What are the chances of this happening? What is the probability? We're looking for a numerical answer. If we start here and go red, red, we go red, red. That's my notation, RR. I calculate that probability by doing the first probability, 0.4, multiplied by the second probability, 0.4. And that's going to give me the probability that I stay in and do my homework, red, red. Okay, and without a calculator again, 0.4 times 0.4. Just think about it, 4 times 4, 16. 1 decimal point here, 1 decimal point here. Your answer is going to have 2 decimal places in. 2 here, our question, 1, 1, that's 2. In here, 2. 4 times 4, 16. That's the probability of you staying in and doing your homework. Now we can write out the other roots as well. If we start back here and go red and then black, R, B. We go 0.4, 0.6. So each time we move along the branches of a tree diagram, we are multiplying. Same situation, let's just do 4 times 6, 24, 2 decimal points, 0.24. Our next one, black, red. So that's black first, then red. It's going to be 0.6 multiplied by 0.4. Exactly the same probability as the first one. The numbers are the other way round. Doesn't make any difference. So that one is 0.24. And our last route through the tree diagram, there are always 4 routes when there are 2 options, is black and black. So I write down B, B. Probability 0.6 multiplied by probability 0.6. 6 times 6 is 36. 2 decimal places in the question, 2 decimal places in the answer. 0.36. That's the probability. It's shown in the tree diagram with the branches and all 4 possible outcomes. We've now got 3 questions about this tree diagram. The first one is, what do the probabilities add up to? 30 seconds, add them up, see what they add up to. Added them up, all add up to 1. Every single time you do this, those column at the end is going to add up to 1. If it doesn't, you've made a mistake somewhere along the line. Next question, what are the chances of doing your homework? Well, you do your homework if you get a red and a red. And we worked out that a red and a red has a probability of 0.16. What are the chances of going to the party? Well, if anything else happens, you go to the party. A red and a red means you stay home. Everything else, you go to the party. You've got 2 ways of working this out. You either add up the other probabilities, 0.24 plus 0.24 plus 0.36, or you just take 1, take away the probability of staying in and doing your homework, which is 1 subtract 0.16. So the probability is 0.84. That's an example of a tree diagram where you are replacing. You had the 15 cards, you picked it up and had a look and put it back in. Let's have a look at another example. The light bulb has gone in your room. It's dark. You're in a rush. There are 20 socks in a drawer. 14 of them are blue and the rest are green. Immediately, let's write that information down. Blue, B, equals 14. Green, G, equals the rest. There were 20 altogether, so there must be 6 green. They added 20. What's the probability of randomly picking a blue sock? Okay, so how many blues have we got? 14. How many have we got altogether? 20. So simply we're going to have 14 over 20, which can be simplified to 7 over 10. If you want to make that a decimal, 0.7. You pick out 2 socks, one after the other. I've got 20 socks, I pick one out, and I pick another one out. Go back. I've got 20 socks, I pick one out. How many are left now? 19. I pick another one out. There's only 18 now. I do not replace. That is going to change the denominators in your tree diagram. So the question is, do you think it's more likely you'll get a matching or an odd pair? Let's have a look at the tree diagram together. So we've got a tree diagram here. It looks very similar to the last one. I want you to fill it in. I'm going to give you 2 minutes to fill in the left-hand side with the probabilities and then go on to working out what's the probability of getting 2 blues, a blue and a green and a blue, and a green and a green. Look back to your last one, follow the pattern, but make sure the socks are not replaced. 2 minutes, off you go. Let's have a look at these probabilities together. So our first one here, I can reveal, is 14 over 20, and our second one is 6 over 20. There were 14 blue socks, 6 green socks. The next stage has changed the denominator. We now only have 19 socks. And we've taken a blue one away, so there's only 13 blue ones left. If we go blue first and then green, the green socks are still the same. So we have 6. But it's over 19 because that blue sock has gone. Let's have a look at this side. A green sock. Have I removed any blues? No, there are still 14 blues. So my fraction here is 14 over 19. Let's look at this. My first sock is a green sock. Green sock gone. There's only 5 left now, but the denominator is still 19. This is the other version. There are only 2 ways the tree diagram can work, one replacing and one not. If we then have a look at the probabilities, we've got them expressed as fractions. We multiply for fractions. You multiply the top, you multiply the bottom, and then you can simplify. So just have a look through those for a moment. Press pause if you want to, and check that you've got the probabilities down, because there's going to be subsequent questions on this. Okay, so 3 questions for you now. First one, what do the probabilities add up to? If we add up the probabilities, once again, they're going to add up to 1. If they do not add up to 1, go back, check. The second question asks, what is the probability of getting 2 socks the same colour? 2 blue, 2 green, doesn't matter, but the same colour. Let's just go back on that and have a look at our tree diagram again. Sometimes it's quite nice to use a highlighter or a different colour. If you get the same sock, colour socks, one root is here, blue, blue, so this probability. Another root is going green, green. So I use the green highlighter, I go green, green, and I've got this. There are 2 ways it can happen. You've calculated the probabilities already. All you're going to do is get that probability and this probability and add them, not multiply. Multiplying is when you're going through the branches, adding is when you're adding up between the branches. So going back to that question, what's the probability of getting 2 socks that are the same colour? There's 2 ways it can happen, and the probability is going to be 0.56 if you add those 2 roots up. The third question asks, what is the probability of getting 2 socks that don't match? 1 blue and 1 green. If we go back now to our tree diagram again, there are 2 ways that can happen. So we're looking for different socks. If I get a blue the first time, then I have to get a green one. Go back to the beginning. If I get green first, then I have to get blue to get a different one. And then actually I've got 2 different possibilities. Both the probabilities, same as before, add them together. If we add up those probabilities, again, you can put them as fractions, you can simplify the fraction, you can convert it to a decimal, and this is what you're going to end up with here. Let's take a read through the next question together. When socks or cards, anything we're talking about, are not replaced, events are called dependent. The probability of this second event is affected by the outcome of the first event. That's why they're called dependent. Suppose you pick 2 cards at random from a pack of cards. It's worth learning about cards because lots of these questions are around cards. In cards, there are 52 cards altogether. That's the total. And we're looking at this question about the probability of it being a king. There are 4 kings. So kings, there are 4. So the probability of getting a king is how many kings? 4 over the total, which is just 4 over 52, which is the same as 1 over 13. You need to draw up a tree diagram to find the probability of getting 2 kings in a row and just 1 king. If you look on your sheet, you've got a tree diagram ready to be filled in with the probabilities in the branches and then calculating the 4 different possible outcomes. I'm going to give you 2 minutes, off you go. Looking at this question, we know that the first time we go to pick from the pack, there are 52 cards and 4 kings. So this box here says, what is the probability of getting a king? We said it before, 4 over 52. There's 4 kings, there's 52 cards. Now, if I go and pick again, there's only going to be 3 kings left. And in total, there's only going to be 51 cards. So that changes, and that's the dependent. The outcome of the second event, the second picking, is affected by your first pick. Let's look at a not king. I pick a king out. Then I go for a non-king. Then I pick a non-king. They haven't changed. So our probability is going to stay the same for that, which is 48, but the denominator changes again because there is only 51 cards. Let's look at our second option. A non-king, 48 over 52, a king, 4 over 51, and a non-king, 47. It's gone down because you've already had a non-king here, and if you take another non-king, there's only going to be 47 of them left. If we have a look at the probabilities, again, you can see to get a king and a king, you multiply across. And these here are 4 probabilities from the 4 different possible outcomes. What do they all add up to? 1. Every single time, probability is adding up to 1. Now, you've got some questions to answer about those. First one, what do the probabilities add up to? We've just said that. That's 1. Every single time. What's the probability of getting only 1 king? What are the possible routes? Go back to your diagram, get your coloured pen. If I start here and I go this way, I've got a king. So my next possible route has to be down to the non-king because I only want 1 king. So that's my route for 1. My second option, if I get a no king on my first one, I must get a king on my second go. And that's my second option. So there are 2 paths, as you've just seen on here, through the tree diagram that end up with 1 king and 1 non-king. So to actually calculate that probability, you're going to simply add up those. So we have 32 over 221. Says here again on the sheet, you might want to write this down. Remember, in tree diagrams, you multiply along the branches, but you add the outcomes of the final column. And it says there, the final column, that are relevant to the given event. So you're having to select which path you're taking through the tree diagram. So we come to the end of the data section on cumulative frequency, box plots, and what we've just been covering, tree diagrams. It's now time for you to take the data assessment. You have 10 minutes. Pause the video. Good luck. Section 3, algebra, are 2 topics that we're going to cover together. First, plotting non-linear graphs and recognising non-linear graphs. The first thing we're going to look at is a graph that has an x squared in. So our example on here is y equals x to the power 2, also called x squared, subtract 3. This is a quadratic graph. We can notice the quadratic is this part here, the x squared. In these types of questions, the first step is to generate the coordinates. You are usually given a table of values. Some of the values are filled in for you, and you will be asked to complete the table. Once you have these values, you can generate the coordinates, which then you can plot on the graph. Let's look at this together. We have a graph of y equals x squared minus 3. We have x values that you can see here run from minus 3 to positive 3. We're going to substitute in the different values for x to find the value of y. Now, we normally start left to right. In this case, I would start in the middle here. Go for your positives or your 0. Those are the easier parts to fill in. So if we have x being 0, we have y equals 0 squared, take away 3. 0 squared, 0 times 0 is 0, so y is just minus 3. And we can see there the value underneath. Let's take another one. Let's take 2. X equals 2. So y equals x squared, x is 2, 2 squared, subtract 3. On the next line down, 2 squared, 2 times 2 is 4, write it down, minus 3 equals 1. So in there, we have 1. Really, really clearly showing your steps, substituting in. Let's do a negative together. Let's do minus 3. So we have y equals minus 3 squared, that's negative 3 squared, take away 3. Looking back at your equation, x squared, negative 3. Let's deal with our negatives first. It's a bit like BIDMAS or BODMAS. Brackets, indices. That's what we've got here. So that's the bit we're going to do first before our subtraction. 3 squared, but in this case we have negative 3 squared. What that means is negative 3 multiplied by negative 3. Let me write that down. Negative 3 multiplied by negative 3. Just look at the numbers to start with. 3 times 3, 9. 3 squared, 9. But we have a negative and a negative. Our rules of negatives tell us that 2 negatives multiplied by together gives us a positive. So we've actually got 9. So this part here is 9, subtract 3, which gives us 6. I'm going to give you 1 minute to fill in the rest of the table on your own. Off you go. So looking at the remaining values we need to fill in, for negative 2 we have 1, for negative 1 we have negative 2, 1 we have negative 2, 3 we have 6. Check you've got those. If not, go back, resubstitute in, be careful of your negatives. So as I said, once this table's completed, we're then ready to plot the graph. Same thing as we covered with our cumulative frequency with crosses, I'd like you to plot the coordinates now. Our first one is going to be -3 on our x value, which is along here, and positive 6 up here. I'm going to give you 2 minutes to plot your points. Off you go. Let's have a look at the graph. So if we plot our points, we can see here from the left-hand side, here, 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 here. This here is a quadratic graph. It has a distinctive shape. You will see in this one that it's a U shape. It's called a parabola. The U shape going in this direction signifies that it's a positive x squared. So the coefficient, the number in front of the x squared, is positive. In this case, it's just 1. We don't see it, and if it's a positive number, we don't write down plus. But this here is positive. That's your U shape. And this is a quadratic function. So what I want you to do now, with a nice pencil smooth curve, down and then up. Off you go. So, next sheet is an exam question. From the top, you have a quadratic equation because of the x squared there. We've got x squared minus 3x minus 1. You have a table of values partly filled in. Your job is to complete the missing points and then plot the graph. 2 minutes, off you go. Let's write out our equation. X squared, subtract 3x, subtract 1. When the value of x is -2, so we have here minus 2 squared. We're going to apply the same rule we did for -3. We then have minus 3 multiplied by another -2 minus 1. All really clear. I haven't done any working out yet. I've just put the numbers in the place of the x. That's substituting. Let's look at the first bit. Minus 2 squared, that's -2 squared, is going to be positive 4. We then have here 3 times 2. We actually have -3 and -2. 2 negatives multiplied together gives you your positive. So we actually have plus 6. And then at the end, minus 1. Go back to the beginning again. 4 plus 6 is 10. Take away 1 equals 9. So in here, on your table, a 9. Then we've got the value when x is equal to 2. Let's do that over this side. So we have 2 squared, take away 3 times 2, that's your value for x, take away 1. Back to the beginning, 2 squared, 4, same as if it's negative. Then we have 3 times 2, but it's minus 3 and positive 2. So that's going to give us -6. 1 positive, 1 negative, answer is negative. Take away 1. Back to the beginning again. 4 subtract 6. 4 go down 6. Going to end up with -2. and then we subtract another 1. On -2, go down another 1, -3. So right here, -3. Each one of those steps, by doing them, you're going to avoid making mistakes, so don't rush through them. Our last one is for 3. So we have x is 3. Let's go over here. So we have 3 squared, take away 3 times 3, take away 1. You can see that that take away 1 is the same for all of them. It's a constant at the end there. 3 squared is 9, take away 9, take away 1. Well, 9 take away 9 is going to end up with nothing, and then we've got -1 on the end, so just -1. There are our table of values. Think, what is the shape going to look like? Is there the number in front of the x squared is 1. It's positive. We don't see it. We don't write 1x. It's just x squared. So we're looking for a shape that looks like this. If we plot our coordinates and it doesn't look like there's 1 out, there's a mistake. You need to go back and check. Let's see what this looks like. So our x value here is -2 and our y value is 9. So our first coordinate is going to go here. Our second coordinate, -1 and 3. You need to draw one on here. If you haven't done this, draw these in as we go. -0 on the x, -1 on the y. Make sure you're getting your x and y around the right way. 1 on the x, -3 on the y, here. We can see that that nice smooth curve is starting to go down here. And then our next point is 2, -3. That's strange. 2 points on the same y value, both -3. Let's have a look at that in a moment. Then we have x is 3 -1. Same one across, next door to each other. And the next one, 4, is up at 3 here. Can you see that it's a symmetrical graph where our 2 lines come? That's going to get you 1 mark, just getting the points on the graph. Our second mark comes from actually drawing the nice smooth curve. So you might want to change your page around as well. If we go from this point and go up here, we've got a smooth curve that way. And I'll do this side, round there. Okay, now this bit at the bottom is really important. As I said, down here at the bottom, the minimum point, they've got 2 points that are on the same, -3. What you need to do there, instead of drawing a straight line across, we don't want something that looks like this. We just want something that goes down and around. So just a little loop at the bottom. That's really important. The next part says use your graph. That instruction is there because you need to go to your graph. To find an estimate, that means not exactly, but your best guess for the minimum value of y. Well, why is this line here, down here? So we're looking for the minimum, the lowest value of y. So what we need to do, you need to get your ruler out again, and we're going to draw a straight line across from where it hits right down here at the bottom. And that's because you've done that little curve bit, which is really important. And it goes lower than -3, and on mine it's estimated to about approximately -3.2. And you'll get something similar when you draw your graph. So that's why that curve bit there at the bottom is really important, and the minimum value. Let's have a look at another one together. This one, the graph is slightly different. Remember, this topic is about drawing non-linear graphs. Linear graphs are just the straight lines, the ones we do with our ruler, the ones that have x in, no x squared. The 2 we've looked at so far are the x squared ones that go like that. They're called quadratics. This one is slightly different. Look at the equation. Y equals x to the power 3. X to the power 3 can also be called x cubed, 3 times. It's like when we work out a volume. Height times base times length, the 3 different ones that you're going to be doing. So this bit here is the cube bit. Take away 7x, add 2. This bit here doesn't matter what. We could be taking away 20x. The key thing is that there's an x cubed in. This is a cubic graph. Write that down on your sheet as well, please. Now there's 3 elements to this. We've got the x cubed, we've got the -7x, we've got the +2. It's quite complicated, okay? So I would suggest that you would do a table that breaks it down. So if you can see here on mine, I've got x cubed, -3x + 2, and then I'm going to add them all up at the end. okay, to make sure we don't make any mistakes. Let's look at the first one together. If we go to here, we have x cubed. That means whatever x is, 3 times multiplied by itself. So if x is minus 3, we have negative 3 multiplied by negative 3 multiplied by negative 3. 3 times. Now, we know 3 times 3 is 9. 9 times 3 is 27. This is slightly different though. Let's just look at the first bit. So if we look here at this bit, it's negative 3 squared. So minus 3 times minus 3 is actually going to be positive 9. We've just seen that in the last example. So that's going to be 9. Then we end up with 9 multiplied by negative 3. So 9 times 3 is 27, but the 9 is positive and the 3 is negative. So actually, the 27 at the end is going to be negative. And all of those cube numbers that are negative to start with, the same for 2 and 1, are going to end up with negative numbers. Then we have minus 7x. Well, if x is minus 3, we have minus 7 multiplied by minus 3. 3 times 7, 21. 1 negative, another negative, 2 negatives multiplied together, 21 is our answer. Still same as positive. Then we've got to add 2. Doesn't matter about what x is, we add 2 all the way. So then we need to sum these. We've got negative 27 here, positive 21, positive 2. So if I'm down on minus 27, I go up 21, I'm then going to be on minus 6. Then I go up another 2, I'm going to be on minus 4. So our end result here is minus 4. So when we come to plot this, I'm looking at this value here and this value here. That's your x and this is your y. Go slowly. You're going to complete the table now, row by row, and then getting your resultant value for y at the bottom. I'm going to give you 3 minutes to do that. Off you go. Let's have a look at the table together. If I just remove these bars here, the best thing to do is to go straight to the bottom line. Check you've got those. So we've got 8, 8, 2, negative 4, negative 4, 8. If you haven't got any of those, press pause, have a look at the table at the top. You can see where you've made a mistake in the actual table. So once you've got that table of values, once again, that's the first step before you then plot. You've got a grid. Check you've got the right values in your table up here, and then I want you to go 2 minutes, plot the points. Don't join them yet, just plotting. Off you go. Once again, you can see here from the graph that a cubic function has a particular shape. It goes like this, goes down and back up again. So what I want you to do now, with your points plotted, I want you to get a pencil, feel free to move the paper around and draw a smooth curve through your points. Off you go. We're now going to look at an exam question together, which is plotting a cubic graph. On your sheet, you will see the equation of the graph, y equals x cubed minus 3x minus 1. The first step is to complete the table, second, to plot the graph, and third, you're going to estimate the solutions for the equation when it equals 1. You've got 3 minutes, off you go. First off, let's look at the table together. You will see on the screen the values for x, minus 2 to 2, and the values for y that have been found by substituting these into the original equation. Once again, if you'd like to copy the previous example whereby you break down the equation into a further table whereby you have x cubed on its own, minus 3x, and minus 1, that's fine as well. Now let's take a look at plotting the graph. If we look at the next screen, we've got our table of values here. We're going to plot these into our graph. So our first point, minus 2 on the x value and minus 3 on the y, that's here. So go across to negative 2 and down to negative 3. Our first point is plotted there. Our second point, minus 1.5 to 0.125. Check the scale on this one, so be careful, you're going up one square and then a little bit further. Our next one is easy, minus 1, 1, both integer numbers, so minus 1 on the x and 1 on the y, it's just there. The fourth point, again, we're on x to start with, negative 0.5 is here, and we're going up to 0.375, so that's up 3 squares to 3, and then a little bit further. Our next one is 0, and then it's minus 1, so our point here. Remember what shape the cubic graph looks like. If we just have a think again, something like this. So when you're plotting these points, think, am I getting the right shape I'm looking for? So far it looks okay. So our next point, 0.5, and we go down to minus 2.3, 3 down, 7.5, which is there. Our next one is 1 and negative 3, which is back down here. Our second point from here is 1.5 and down again, negative 2.125. And our last point to plot is 2 on x and 1 on y. Once you've got those points plotted, we need to make sure that we join them in a smooth curve. So again, you might want to change the orientation of your paper so that you can get round. So what we're going to do is up here, down here, and back up again. Again, making sure you're using a pencil. Any mistakes you can redo. Let's have a look back at that third question here, part C. Use your graphs. We're going to have to be doing something on the graph to estimate the solutions of the equation we have when it's equal to 0. Now, we had a look at these before. When this is equal to 0, the y line of y equals 0 is actually the x-axis. We saw that in a previous question. So if I just draw that line on, and I'd like you to do the same, please. I want you to draw a line across the x-axis at x equals 0. So we have here a line that goes all the way through here, which is just the axis line. And each time that this line cuts our cubic function, there's going to be a solution. So we've got one solution here, another solution here, and the third solution here. Again, when we're getting a cubic graph, we're going to get 3 solutions, 3 values for x. So our first value, remember these are estimates as well, so our first value of x is minus 1.5. There will be a range as well on the mark scheme, so it can be a little bit less, a little bit above, given your own drawing. Our next one here, we go to our 0 and we count along 1, 2, 3. So that further value for x is going to be 0.3, and that's a negative value because it's left of the 0 for x. And our last solution is going to be positive. It's over the far side here. It's about 1 square before 2, so that's going to be 1.9. So they're the 3 solutions that you find by plotting your graph and then looking at where the graph cuts the x-axis, which is actually the y equals 0 line. Having just looked at quadratic and cubic graphs, we're now going to look at how we can use these graphs to solve equations. Let's have a look at this example here. Solve the equation of 2x squared subtract 5 equals 3x. We've got the x squared in there, therefore it's a quadratic graph. We can do this by considering the left hand and the right hand side of the equation separately as 2 functions. So what you've got down on your sheet of paper is 2x squared minus 5 equals 3x. We're going to make these 2 separate functions. To do that, we're going to make them equal to y. So on the left-hand side, y equals 2x squared minus 5, and on the right-hand side, y equals 3x. Write that in now. The point where these 2 functions intersect is going to give us the solutions. Now, it might be the case that you're going to have to actually draw the graph, like we've just done, and then look at the intersection. Or the graphs will be presented to you, and you'll have to look at the intersection points. So if we look here now at the 2 graphs, you've got these on your table. We've got our graph like this, which is our quadratic. We've got our straight line, which is our linear. they cross. I want you now to take your pen and I want you to look at these crossing points. We have a crossing point just here. Circle it. We have another crossing point here. So these two graphs are intersecting at 2 points. We want to know the coordinates of this point and the coordinates of this point. If we look at those, our point here is -1, -3. That's x, then y. Up here on our x, we go across 2.5, and we go up on our y to 7.5. So the x value of these coordinates give us the solutions. So when it says solve this graph, what we're looking at is x equaling -1 and x equaling 2.5. So if we draw lines from these, you can see clearly our x values. So on this side, we have x here being 2.5, which is a solution, and our second solution here is x equaling -1. A quadratic graph always has two solutions. Let's look at another one. So we've rearranged it now so that we have all of our terms on the left-hand side, which leaves on the right-hand side 0. We can then make two new equations, just like we did before. Y equals 2x squared minus 3x minus 5. And y equals 0. Now y equals 0 is a special line. If you've got your axes and you go to y as 0 and you draw a line across, actually the y equals 0 line is just the x-axis. Write that down. So this means that the solutions to the equation that we have up here, 2x squared minus 3x minus 5 equals 0, can be found when this quadratic that goes like this crosses the x-axis. So we're looking here now, we have two crossing points. Once again, a quadratic has two crossing points. Let's label our crossing points. Here and here, as we did before. X equals -1, x equals 2.5. Just what we found before. So it's the same solutions, x equals -1 and x equals 2.5. Let's have a look at a different graph now. We have a cubic graph. X cubed minus 3x equals 1. The equation does not have exact solutions, so the graph could be only used to find approximate solutions in this case. A cubic function can have up to 3 solutions. Remember, quadratic has 2. Quadratic graphs are x to the power 2. Cubic graphs are x to the power 3. 3 solutions. So the graph tells us how many solutions there are. Again, we can consider the left-hand side and the right-hand side of these equations separately. If we rearrange these as we've done, we have here on the side y equals x cubed minus 3x, and on the other side y equals 1. Look at the graph on your following page and we have 3 crossing points. Let's mark them here, here and here. You can see here that our 3 points are going to be approximate. Okay, so if you approximate those, what we're looking at, you're drawing a line down. Again, use your ruler, it'll be helpful. So from each one of these points, drawing a little line down to our x value, x-axis, and down. And again, you'll estimate these values here. So check, yours have come out x equaling -1.5. That's the first point on the left. Then we have x equals -0.3, and further over, just a little bit less than 2, x equaling 1.9. So 3 solutions that are approximate on the cubic graph. We're now going to briefly look both at our cubic and quadratics again, and some further graphs. Now this part is about recognising. You will not be expected to plot accurately these graphs beyond the cubic and the quadratic, which we've already done. What you're going to have to be able to do is look at a graph and say that is a and y, and then we need to know the distinctive features of each of the graphs. So we're going to go back to the beginning where we started, quadratic. A quadratic function always contains the term x squared. Really, really important. Doesn't matter whatever else it includes. If it's got that, and that's the highest power of x, it's the highest one, then it's going to be a quadratic graph. It can also have x's in, and it can also have constants. Constants are just numbers. So if you're not sure about that word, just give it a circle and write down next to it numbers. That's what the constants means. So here are examples. I said at the beginning that this one here, where the coefficient, the number in front of x squared, is positive. Here it's just 1, here it's 1 as well. It's going to be a U shape. So this direction is positive. The third example here, the coefficient, the number in front of x squared, is -3. So this way is a negative. And some people remember it by saying if you're positive and happy, you're going to be smiling, so it's going to be this way. And if you're sad and negative, you're going to be unhappy, so it's going to be a smile in the opposite direction. But really, it's a U shape for positive and an N shape for negative. And when you plot them, that's the functions you're going to get. Again, it says there, the word I mentioned before, the characteristic shape of a quadratic is a parabola, and that's the word there, spelt. Cubics. Once again, a cubic function contains the term, circle it, x to the power 3. It can have x squared in, it can have x, it can have numbers in. But if it has an x cubed in, which is the highest one, it's going to be a cubic. And again, we've got some nice graphs here. This one's a positive and this one's a negative. You'll notice them because they sort of have this shape to them, particular. The next one you need to be able to recognise is called a reciprocal graph. Okay, and these always contain a fraction with a term x in the denominator, so the number at the bottom. So look here, we have y equals 3 over x. X is in the denominator at the bottom. Y equals 1 divided by x. 1 over x. X is at the bottom. X is at the bottom. All of these ones has a fraction with x in the denominator. In each of these examples, the axes, that's both the x and the y axes, form asymptotes. And that's a word to describe the fact that the curve of the reciprocal graphs never touch them. You can see in both examples, especially this one in the middle, that the graph, the curve comes very close, but it will go on and on and on into infinity and not actually touch the x-axis. Another type of graph that you're going to have to recognise is called an exponential. An exponential function is in the form of y equals a to the x. So the power is actually x. And the a part here is just a positive constant, a number. So for example, 2, 1.5, but it's positive, okay? And you can see all of these along here. We've got 2, 3, 0.25, it can be a fraction, it doesn't have to be an integer, but we have x in the power. And similar to the reciprocal graph, the x-axis, not the y one, the x-axis forms the asymptote. That means the curve never touches the x-axis. Look at the three examples and then have a look and see how they compare to the reciprocal graphs. The final kind of graph that you're going to have to recognise is called an equation of a circle. Now, this here is the formula that it's going to have. It's going to have x squared in, which you'd have in a quadratic, but it's also going to have a y squared and an r squared. And the r squared is the radius in the actual circle. But what I want you to focus on is just these three elements having to be present within the equation. Now r was going to be a number, might be 5 or something, but it's your x squared and your y squared you're looking for. So on your next sheet you have 6 graphs, 6 equations. Your job is to match the equation with the graph. I'm going to give you 3 minutes, off you go. Let's take a look at these 6 graphs then. Our first one up here is just a straight line. Nothing special. It has no x squared in, no x cubed, it has no powers, it's going to be a straightforward graph. Now you might notice from your knowledge of linear graphs that it actually has a negative gradient. If you start off here on the left, it's going down. It's the only linear graph and it has a negative gradient. It is going to be this one. So let's write in y equals negative 2x minus 3. This topic here is the y equals mx plus c. That's linear graphs if you want to revise that. Let's have a look at the next one. It's got that wiggle on it. That's going to be a cubic graph. So that's got to be this one here. Y equals x cubed. So the third graph we have is going to be a reciprocal graph. We can see here we have a curve and a curve. A reciprocal graph is in the form where it has a number, for example 3 over x. So we could have y equals 3 over x. So the x is in the denominator. Looking at our graphs, there doesn't appear to be an equation that looks like this. So perhaps one of these graphs has been one of these equations has been rearranged. We're going to come back to the reciprocal one a bit later. Let's go on to the fourth one together. This one starts along here and goes up. And this is an exponential graph. The curve forms an asymptote to the x-axis. And we know from our notes that we've just gone through that an exponential graph has a constant, a positive number, to the power x. And the only one of the equations that is this one here. So we have y equals 4 to the power x, an exponential graph. Our fifth one is easy. That one's a quadratic. So we're looking for here, we're looking for the x squared. It's going to be this one. It's not this one because there's also something else in there that we'll look at in a moment, the y squared. So this one here is going to be y equals 3x squared. Positive again, the U shape. And our last one we can see is a circle, and it's going to be this one here that we've just gone through. So we have x squared plus y squared equals 3 squared. The 3 is the radius. If you look at the centre of the circle and you just count along, you can see that there's 3 squared there. That's why you've got your 3 squared. But you're identifying it because there's an x squared and an y squared added together. Now this just leaves our last equation here, which is actually yx equals minus 3. Now that has to match with the one that we left out, the third one, which is this one here, which is the reciprocal one. And as I explained up here, it needed to have x in the denominator as the fraction. This actually can be rearranged to make this equation here. We have xy, which is x multiplied by y. If we do the inverse operation by dividing by x, we have y equals minus 3 divided by x, which looks more similar to what we looked at. So be aware for that some of the equations may need to be rearranged so that you can match them. So now we've had a look at graphs, both plotting them and recognising them. As I mentioned at the beginning, the two graphs that you need to be able to plot accurately are the quadratic and the cubic graphs. You may then need to be able to find solutions from them by looking at points where they intersect. A further aspect to the non-linear graphs is to be able to identify graphs such as the exponentials, the reciprocals, and the circle. We're now going to take the algebra assessment. Press pause on the DVD to start your assessment. Good luck. Our next section is on shape. We're going to be doing two topics. First, trigonometry, and second, circle theorems. Before we start on the trigonometry, it's really important that you know how to use your calculator. So on the screen I have a picture of a standard calculator that is used at school. Your calculator may be different. I also have a calculator with me which will be showing you some of the buttons on here. But it's really important that you can identify the following buttons that I'm going to highlight now. So across the top here, we have something called sin, cos and tan. And these buttons will have their own sin, cos, and tan. Above them, you will see the words written sin to the -1, cos to the -1, and tan to the -1. They're called the inverse functions, and I'm going to explain when we use them and how we use them in a moment. But just to make sure you can see where these buttons are. And to get to the ones at the top, which are the inverse ones, these ones, you generally have to press a shift button or a second function. So on my calculator, I've got them here, sin, cos and tan, and to be able to get my negative, sin to the -1, cos to the -1 and tan to the -1, I'm going to have to press my shift button up here. So in some of the calculations I'm going to be going through this with you, I want you to have your calculator out and doing every single calculation with me on your calculator. Another really key point is to be able to distinguish when a question is about trigonometry. If you look here on the screen, we have a triangle that is a right angle, and it has an angle labelled. You will also remember a topic called Pythagoras' theorem, which is also about triangles and also about right angle triangles, but it does not involve any angles. That's the difference. Another way to think about the two questions is that Pythagoras being C grade generally appears earlier in the paper. So when you're doing the higher tier paper and trigonometry is a B grade, it's likely to come later in the paper. It's also likely to be on the calculator paper because, as I explained, you need to be able to use your calculator for this topic. However, be aware, sometimes questions have both Pythagoras and trigonometry combined. We're going to look at trigonometry now. Our first step is about labelling the triangle, the sides of the triangle. I've got them labelled here, and I want you to label this at the same time as me, filling in the gaps. Our first side is our hypotenuse. You'll know that from Pythagoras. It's the side opposite the right angle. Our right angle is here, our 90 degrees, and it's the side opposite, not the sides touching. Really important, always opposite. Label that one first. It's going to be the easiest one. Go to the right angle, draw a line across, that's the hypotenuse. Now, you're not going to want to write out every time hypotenuse. So what you might want to put down is just a capital H. Nice and easy. The next side I would always recommend you to do is the opposite side. Opposite the angle. In this example, we have an X here, labelled. The side opposite the X is going to be all the way over here. And we call that O. Again, no need to write down opposite, just put an O there. And the leftover side is the adjacent side, put down an A. The adjacent side means it's next to the angle. So you can see here that this line touches the angle. But when I do it, put in your hypotenuse, put your opposite side, and the leftover one is always the adjacent. That's going to be really important. So when you see these questions, just start with that. So, on your next sheet, you've got 4 triangles. I'm going to give you 2 minutes. I want you to label up all of the triangles, hypotenuse, opposite, adjacent. Off you go. So if we look at these triangles together now, the first side, hypotenuse. Go to your right angle, draw a line across. That's my hypotenuse. I'm going to do all my hypotenuse first. This one is red, hypotenuse. The yellow one is here, and the purple one is here. The next side I'm going to label up is my opposite. Opposite the angle, not the right angle, the angle that is labelled. So here we have, and it's going to be opposite. Here we have the angle, go across, opposite. Here we have our angle, go across, opposite. Last one, angle here. And our last side is our adjacent side. It's the one next to the angle. It's the leftover side. A, and A. First step, label your triangle, all of the 3 sides. We then need to decide which one of these buttons on our calculators, which is actually a trig ratio, sin, cos or tan, we're going to have to use. We can make that decision based on the information we are given in the question around labelling. What I've got here is something you may have heard before. It's a big long word called SOHCAHTOA. It has 3 elements to it, which I've broken down here on the page. The first bit, so, second, ka, and the third bit, toa. Now, you might recognise some of these letters from what we just labelled our sides with. We have O here, opposite, H here, hypotenuse, A here, adjacent. So out of all of those letters, you already know 6 of them. The S stands for sin, which is here. The C stands for cos, and the T stands for tan. They're the 3 buttons across your calculator as well. Now, SOHCAHTOA is just a way of remembering which trig ratio to use. So if we have a look at the 3 triangles across the top here, we're going to label them. So they all look very similar. We have 37 here, and we've got 5 is the hypotenuse, hypotenuse, hypotenuse. The one opposite, 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 they're all the same, O, O, O. And our other one down here is A. So label those along the same time as me. Now, grab a different colour pen. Look at your first triangle. The hypotenuse, H, has 5 centimetres on. The O has an X on. They've got something on the sides. The other side doesn't have anything, so cross out the A. Let's look at the next triangle. H has got something, A has got something, O, there's nothing there. You added the O, cross the O out. The next one, O's got something, T's got something, the hypotenuse is blank. Cross the hypotenuse out. That's the process you're going to go through. You're going to label, and then you're going to cross out the side that doesn't have anything on, the side you're not interested in. And then you're left with 2 sides. So on the first one, we're left with O and H. That's the SO. That's the sin. The next one, we're left with A and H. That's the cos. And our last one, we're left with O and A, which is tan. And from that, which 2 sides you've got left, you can work out which ratio. Is it sin, cos, or tan? Once you've decided that, you then have an equation, which you can also remember from the SOHCAHTOA. Sin, O, H. And we write the first one, sin equals O, because O comes before H, divided by H, hypotenuse. And these 3 things are going to help you work out the missing side or the missing angle. One last thing, we're going to go through one of these questions all the way from the top, so it's going to become clear. But one thing I just wanted to share with you is some students find rewriting these formulas using triangles helpful. So I'm just going to explain in case you would like to follow that method as well. If you do a little triangle, some students use these in science. The first box is S, the second box at the top is O, and the third box is H. It's the same way we say it, SOHCAHTOA, so S, O, H. And the next one will be C, A, H. Now what you can use this for is to be able to find the missing one. So if you wanted to find O, cover up O, so cover up, and then you look at S, you do sin times hypotenuse. If you wanted to find the hypotenuse, you would cover that up and do opposite divided by sin. We'll use one of these in a moment, but just to let you know, if you like these triangles, then I show you the other ones, which is C, A, H, and the last one here, which is tan, O, A, tan. So then when we've got our trig ratio, we then substitute in, and then we're at the answer. But the main point first is labelling the triangles and identifying which ratio we're going to use. So if we have a look at just one triangle, I've got the triangle here. Same process again. It's the same triangle, so you're familiar with it. This side is hypotenuse, this side is opposite, this side is adjacent. Which side doesn't have anything on? Adjacent. Let's get rid of it. Cross it out. We've got O and H. I think of SOHCAHTOA. Which one has O and H in? Ka has A in, Toa has O in. Toa has A in. Both of those are no good, so it's going to be the sin ratio. So I might then write out sin x equals O over H. YO first because SOHCAHTOA, S-O-H. So it's O, the opposite, divided by hypotenuse. Okay, so sin is always attached to the angle, cos or tan. So in this case, we know our angle is 37. So we have sin 37 equals O. What's O? X. We don't know it, so we write in X divided by the hypotenuse, 5. We do know the hypotenuse, which is 5. So we've got sin 37 equals X, we don't know, divided by 5. Well, to be able to find X, we just need to multiply our sin 37 by 5. So rearranging that, we then have X equals sin 37 multiplied by 5. This is when you need to take your calculator. So into your calculator now, sin 37 multiplied by 5. And you're going to get a big, long number. So these questions are going to require roundings to significant figures or decimal places. But you'll be explicitly told, give your answer correct to, and the most popular one is 3 significant figures. So that's what we're going to use throughout our trigonometry section. First off though, when I've got my value, I write down everything. So you're going to do the same. Check on your calculator whether you've got 3.009075116. That's what we're looking for. If you haven't got it, you might need to reset your calculator at the back to check it's in degrees. Then we're going to round to 3 significant figures. Let's check everyone knows how to round. Start from here. 1, 2, 3. Draw your line. Look at this number, 9. It's a big number. So the number before is going to increase. So our answer to 3 significant figures is 3.01. 1, 2, 3. 3 numbers in your answers, 3 significant figures. It's in centimetres because we're finding a length. Add centimetres on the end. That bit is easy. The bit where you're substituting in and putting in your calculator, the first step is it sin, cos or tan? Get that decision right. Let's go through an example of cos. Once again, label up your sides. Opposite, hypotenuse, adjacent. Which one don't we want? Well, the one without anything on is the O side. So we have A and H. That's why we're going to use cos. Let's write it out again. So we have cos X equals A divided by H. Do that step. Don't just skip straight to adding the numbers in, okay? This is demonstrating to the examiner that you know it's the adjacent divided by the hypotenuse, and in case you put them round the wrong way, there's still marks available for you. Remember, the cos part is going to be associated with the angle. Again, it's 37. We're using a similar example. Cos 37 equals adjacent. I don't know it, so I write down X divided by hypotenuse, which is 5. How are we going to find the X? Rearrange, multiply them together. We write it down. X equals cos 37 multiplied by 5. To your calculator. Cos 37 multiplied by 5. Again, big long number, you write it all down. 3.9931775. Rounding to 3 significant figures. Start on your left-hand side. 1, 2, 3, straight line. Look at this number afterwards, 3, small number. So the 9 stays the same. So the length of the adjacent side is 3.99 centimetres, correct to 3 significant figures. Again, identifying its cos, substituting in. The last one we're going to do is for tan. Same process. Label, hypotenuse, opposite, adjacent. Which one don't we need? Hypotenuse has nothing on, crossed it out. Then we're going to look O and A. Which one? SOHCAHTOA. Sin, cos, tan. Which one has O and A in? It's the last one. It's labelled up here, TOA. So we have tan X equals O divided by A. We're then ready to substitute in the values. Tan X. Tan is going to be associated with the angle. So tan 37 equals opposite. Oh, I know what the opposite is, so I need to put that in. So the opposite is 3. So write in 3 divided by adjacent, which is X. So now you'll notice that the x is actually in the denominator. The other two examples, x was in the numerator, so we just multiplied our two values together for the tan and what was in the denominator, and we found our answer. This time it requires a little bit more rearranging. So if we multiply through by x, we're going to have tan 37 multiplied by x equals 3. But we need x on its own. So we're going to have to get rid of the tan 37 here by dividing through. So we have x equals 3 divided by tan 37. And we can put that into our calculator and get our answer. But let me just show you, this is the point where some students like to use the triangle. So if we just put that triangle over here, we have tan OA, tan opposite adjacent. In this example, we're actually trying to find the missing side, which is the adjacent. So if I cover up the adjacent here, and you might like to put your finger on it, you can then see that it says O here divided by T, which is what we're doing, 3 divided by tan 37. This way over here is fine, but you also might like to use the triangle. It's up to you as to what you prefer. So let's put that into our calculator and see what we get. 3 divided by tan 37. Notice we haven't used any of the inverse buttons. We're just using sin, cos or tan at the moment. And our number comes out 3.981134465. 3 significant figures. Let's count along. We've got 1, 2, 3. Draw your line. 1's a small number, so the numbers in front stay the same. So actually x equals 3.98 to 3 significant figures. So that's going through sin, cos and tan to be able to find lengths. Let's look at a real example. In your next two sheets, you have 4 triangles. I'd like you now to spend some time with your calculator, writing down, labelling the sides, identifying which trig ratio and finding the missing length. Press pause. I'm going to give you 4 minutes to do this. Off you go. Our first triangle, we are going to start by labelling the sides. We go to the right angle and we go across to the hypotenuse. We go to the angle labelled 65, across, opposite. And our leftover side is adjacent. Next step, what don't we want? A. There's nothing on the A side. So we're left with H and O. Again, you might want to write SOHCAHTOA down on the side. Perfectly fine to do in your exam so you remember. O, A. Which one has O and H in? It's our first one there. It's sin. So let's write down. What are we looking for? We have sin x equals O divided by H. Substitute in your values. Sin 65, the angle labelled, equals O, don't know, x, over hypotenuse 11. How are we going to find the x? Multiply them together. Write that down. So we then have x equals sin 65 multiplied by 11. To your calculator, sin 65 multiplied by 11. Again, long number, write it all down. We have 9.9693856557. 3 significant figures. Get your pen out. 1, 2, 3. Draw my line. This number's a big number, so the 6 is going to go up to 7. So we've got 9.97 centimetres. Next question. Again, we're going to label our sides. We've got our hypotenuse here, we've got our opposite here, and we have our adjacent here. Which side are we not using? It's the opposite. Cross out the opposite. Now, we've got to think about our SOHCAHTOA, and we've got A and H. So we're going to be using cos. Let's write it out. Cos x equals A divided by H. A comes first. C-A-H. Substitute in your values. Cos 53 equals A. What's A? 6. Divided by H, we don't know if that's what we're finding out, X. Okay, X is on the bottom now, so we're going to need to do some rearranging. So we can go X multiplied by cos 53 equals 6. We then need to isolate X. We want X on its own. So this here, our cos 53, needs to be divided through. So we have X equals 6 divided by cos 53. To your calculator, 6 divided by cos 53. Big long number again. We write it all down. So we have 9.969840847. We're going to be rounding again. 3 significant figures. 1, 2, 3, straight line. 9 is a big number. 6 is going to go up to 7. So 9.97 centimetres. If we just have a quick look at that in the context of the question, we are saying that the hypotenuse is 9.97 centimetres. Would I say that's about right? How do I know? Look here, the hypotenuse is always the longest side, so it's got to be longer than 6. So if 6 is the adjacent, we must have a hypotenuse bigger than 6, and it'd be unrealistic if it was lots bigger than 6. So 9.7 seems a reasonable answer. It's a good check to do. Okay, the next 2 questions you were asked to do, we're going to follow the same procedure again. So we've got hypotenuse, opposite, adjacent. Cross off the one side that has nothing on, this one. And we've got O and H. Decide the trig ratio, sin, cos or tan. It's going to be sin because we have O here and H here. So we have sin x equals opposite divided by hypotenuse. It might seem laborious, but carry on writing down the full trig ratio. Remember, in the exam, you're only going to be doing this once, and you need to demonstrate to the examiner you know how to do it. So we then have sin, the angle, 54, equals O, that's 8, divided by the hypotenuse, which is x. We don't know that one. We're going to try and find it. The hypotenuse needs to be bigger than what? Have a look. 8. It needs to be bigger than this 8 here. So we're looking for an answer bigger than 8. Rearranging, we then have x sin 54, that means x times sin 54 equals 8. Rearrange again, we have x equals 8 divided by sin 54. Type that into your calculator. And we have the answer 9.88854382. Bigger than 8? Yeah, so we're in the right region. Round that number to 3 significant figures like we have been doing. 1, 2, 3. Draw your line. 8's a big number, so the number before is going to go up. 9.89. Okay, last one of finding the lengths. You're doing well. Cross this side, opposite, hypotenuse, adjacent. Last one, crossing off which one we don't need. We do not need the hypotenuse. There is nothing on the hypotenuse. We have O and A, so we're going to be using tan. We write out our ratio. Tan x equals O divided by A. Substitute in our values. Tan, what's the value of our angle? 71. Equals O. O is what we don't know. That's your x. Divided by A. A is 4. Okay, then to find the x, we can see here that we're going to simply multiply tan 71 by 4. So we have tan 71 multiplied by 4 is going to give our value of x. To our calculator, tan this time, 71 times by 4 equals 11, writing it all down, 6.6168435. Let's go and round that. 3 significant figures. Starting here on the 1. 1, 2, 3. Draw your line, look at the 1. 1 is a small number, so your 6 stays the same. 11.89. 0.6 centimetres rounded to 3 significant figures. We're now going to look at a trigonometry problem. This problem's about a ladder. So we've got a 5-metre ladder that's resting against a wall. And you can see from the picture there, 5 metres, the ladder resting against the wall. And this makes an angle of 70 degrees with the ground. So the 70 degrees here is actually referring to this angle. And we can see our right angle, if you want to draw it in, is just here. So immediately, we've got a trigonometry problem. It's not Pythagoras because we have an angle labelled of 70, but we're still finding lengths in its right angle. So first step is always the same. Let's label the triangle. We have our hypotenuse here across the side from the right angle, which is our 5-metre one. We have our angle here, which is 70. Across from there is the wall, which is the opposite, and x here is the adjacent. The question asks, what is the distance between the base of the ladder and the wall? So that is actually, the distance we're looking at is here to here, which is labelled x. So we're actually trying to find the adjacent side. So it says here to find the length of the side adjacent to the angle given the hypotenuse. What we're going to use, which one do we not need? We do not have anything on the opposite side. So the opposite side is what we are going to cross out. We are then left with A and H. So, ka, toa. Which of the three has A and H in? It's the middle one, cos. So if I just reveal here, we're going to be using cos. This here is something you may have seen. It's called theta. It's a Greek sign. But it's the same thing as saying the x. It's the angle, okay? So as we've done, it's going to become cos 70 for the angle. Then if we remove this thing, we're going to have substitute in our values. Cos 70 equals x. We do not know A, but we do know the hypotenuse 5. We're going to rearrange that to give us x equals 5 multiplied by cos 70. Put that into your calculator, you're going to come out with 1.71 metres, and that's correct to 2 decimal places. It's no different to the problems we've just solved, but it has some words around it, pictures, maybe some context of a ladder, but it's identical. We did nothing different mathematically. Okay, so as soon as you spot trigonometry, follow those steps of the labelling the triangle, identifying the ratio, substituting. We're now going to look at some questions that involve finding angles. I mentioned at the beginning that on our calculator we have the buttons of sin, cos and tan, but we also have 3 buttons above them by pressing our shift or our second function button, which is sin to the -1, cos to the -1 and tan to the -1, which is called the inverse functions, and those are used for finding angles. Let's have a look at this here. We've got a right angle triangle. It has an angle labelled there, the theta. Can be x, it's not a problem. This is 5 and this is 8. Before we do anything, we do our first step. Grab your pen, label your triangle. Hypotenuse, opposite, adjacent. Our second step, which side has nothing on? It's the hypotenuse. So we're going to cross off the hypotenuse, and we know we have O and A. So, ka, toa. Which one of those is O and A? Tan. So if I pull back this, it will have some explanations. It says here, we are given lengths of the sides opposite and adjacent. We've identified those, 5 and 8. So we're going to use tan. So tan x or tan theta equals the opposite divided by the adjacent. Let's substitute in our values for that. We know that the opposite is 8, it says here. We know adjacent is 5. When we're at this situation, it's always going to be the same for the angles. You might have sin equals 2 numbers. What you need to do on your calculator is you need to press your second function or your shift. You need to work out what that is. So on mine, it's the shift button. So I'm going to press shift, and then I'm going to press the same button as tan. So once you've pressed the button on your calculator, on your display will show tan to the -1, okay, to a power -1. You are then going to need to use brackets. So we have tan to the -1. I'm going to rewrite it out here. Tan to the -1. Open brackets, 8 divided by 5. And remember, that line across is just divide. So on my calculator, open bracket, 8 divided by 5, close bracket, equals. And I've got an angle of 57.99461679. Again, I'm writing down all the values. Does an angle of 57 seem reasonable for a triangle? Well, we know already that one of the angles is going to be 90. All the angles add up to 180. So if 90 is one of them, the other two have got to add up to 90. One being 57, about 60, and the other one being about 30. Yeah, great. If you had an angle that came out of more than 100, and we've already got a right angle, you know there's been a mistake. So again, think about your answers. Do they make sense? And if you round that, as it said in here, to 2 decimal places, you're looking at 57.99. And it's shown there nicely as typed out with what you're going to type into your calculator. So doing the angles is no different. First step, second step. All you need to do is press your button on here, which is going to be an inverse. And then make sure you use the brackets. So lastly, what we're going to look at together is a problem. And it's worth 6 marks. So quite a big question in the exam. I'm going to read through it once with you, and then I'm going to leave you to have a go. So we can see here that ABC is a triangle. That's the big triangle. We can see that ADC is a straight line. That says across here, this line here is a straight line. And it says it's perpendicular with BD. That's that line there. That means that this line and this line, perpendicular, means they meet at 90 degrees. So it's forming, on this side, CBD, a right angle, the 90 degrees, and on this side, another triangle, BAD. In the question, it tells you the lengths 7 and 12, but they're labelled on the triangle, and it gives you one angle. I see an angle, I think trigonometry now. Calculate length of AC. So what they actually want you to find out, AC, is this line that goes all the way across the triangle. That's what you're trying to find out. And it says, give your answer correct to 3 significant figures. So you've got 5 minutes for this one. Start from the top, think about your trigonometry, but also think about other knowledge you have from previous topics that may well be related to this question. Off you go. Let's have a look at this question then. I've got the triangle here, and I've got labelled up exactly what we're trying to find. We're trying to find the whole length across A to C. But actually, looking at this triangle, we can see that there's 2 triangles. If we look on the left-hand side to start with, I'm just going to redraw what I can see. So I've got a triangle that goes A, D, and B. It's good to keep the notation and the same letters because it shows that you are referring to the triangle. We've got a right angle there, we have 65 degrees here, and we have 7 here. Now with that piece of information, I've got an angle, I've got a side, I can find one of the other sides by using trigonometry. So I'm going to find this side to start with. I'm going to call that my x. Label up my triangle, same thing, hypotenuse, opposite, adjacent. Which one am I not using? I'm not using the adjacent. Cross that one off. I've then got my hypotenuse and my opposite. So, ka, toa. Which one has O and H in? Sin. So let's write it out. Sin x equals O divided by H, which equals sin 65 equals O, we don't know, that's your x, divided by our hypotenuse, which we do know, just lost, is 7. How do we find x? Multiply them together. So we have 7 multiplied by sin 65 equals x. To my calculator. So 7 multiplied by sin 65 equals, big long number, I'm going to write it all down, 6.344154509 equals x. Okay, so rounding that to 3 significant figures, we have 6.344154509 6.34, because the number after the 4 is 4, it's a small number. So if we look back here now, we now know B to D. We know B to D is, as we've just put down there, 6.34. So let's add that to our original diagram, 6.34. And that's our B to D. Okay, that might be helpful for something else in a moment, but actually there's still something else I can find on this triangle. You see here the line that goes from A to D. I want to find that because that's part of A to C. So I'm going to go back to that triangle and redraw it over here. And I've got this here. So I have 7, my right angle, and here 6D5. I know this one now, I can write it in, but actually this is the one I'm looking for, and that's what I'm interested in. So, label up, hypotenuse, opposite, adjacent. Which one don't I need at the moment is the O, cross it out. Back to the same thing, which trig ratio? SOHCAHTOA is going to help us identify it's the cos one we're looking for because we have A and H, hypotenuse and adjacent. So, looking at that, we have cos X equals A over H. Notice I'm still writing out the whole thing. You need to be doing that as well. Then we have cos 65 equals adjacent. We don't know that. That's the X over 7. How are we going to find the X? Multiply them together. So we have cos 65 multiplied by 7 equals X. Back to the calculator. Cos 65, type it in at the same time, multiplied by 7 equals 2.958327832. Let's round that together now. 1, 2, 3. Look at the next number, 8. Big number, 5 goes up. So we've got 2.96. Add that back to the diagram. So back up to your top, your original document here. This one, I'm just going to put it here because I've got the room, is, as we said, 2.96. So out of all of the lengths, there is only one length we still haven't found, and that's the D to C length. And if we find that, we can add it to the A to D, and we're going to then find the A to C altogether. So this is the length I am now interested in. I know this one is 12 and I know this one is 6.34. There's no angles labelled, so I'm going to go back and think about Pythagoras. So this is an example of a question where we have both trigonometry and Pythagoras embedded in the same problem. No one told us. This is what we need to spot. So looking here, if you cover up this triangle on this side and just focus on this, the BDC, I'm going to redraw it. You're going to do the same. Let's have a look here. So our second triangle, our triangle on the right, is like this. Here is 6.34. We found that out. We don't know that one. That's what we're trying to find. It's the one that goes from D to C, and that's B, and that's 12. So Pythagoras' theorem, to find the missing one, which one is the hypotenuse? Well, this is our right angle, so the hypotenuse is the one over there. So we're going to square our two sides and we're going to subtract because we have the hypotenuse. So we have 12 squared equals, we can do that without a calculator, 144. And 6.34 squared, which you're going to have to use the calculator for, 6.34 squared equals 40.1956. You need to write down everything you're typing into here needs to be replicated on your paper. So we're going to subtract that now from 144. So for 144, subtract the answer. It's going to give me, I'm going to write it down before I do anything else, and I'm going to say that I'm subtracting, is 103.8044. That's not the value of x, that's the value of x squared. So to be able to find the value of x, I'm going to have to square root that. So again, I haven't touched anything on my calculator. This number is still sitting there. I am then going to square root that. So this is another button you need to find on your calculator, which you would know from Pythagoras. I'm going to square root my answer, and it's going to come out with 10.1884443. I'm going to round that to 3 significant figures, which is going to be 10.2. Is that reasonable? So the hypotenuse is 12. The hypotenuse is the largest side. If that's the largest side, our value for x has got to be less than 12, and it's 10.2. Sounds reasonable. So let's go back up to our original diagram. We've done all our working out, and we now know that this line here is actually 10.2. We now have all of the sides in the triangle. We can answer the question that was given in the original question, which was work out the length A to C. So for A to C, we're going to take this number and add them together. So once again, let's find some space. We have 10.2, add 2.96. Notice how I've just put down my decimals there. I'm lining up the points. Okay, yes, I've got a calculator, but I can do it manually. 6 add 0 is 6. 2 add 9 is 11. Put my decimal point in. 3, 1. So the length from A to C equals 13.16. Make it clear to the examiner. Find a space. Write it down. AC equals 13.16 centimetres. And you're done. It was worth 6 marks, so it's going to take you at least 6 minutes in the exam. So don't rush through it. Think about everything you know about the particular topic and any related topics. And as I mentioned, trigonometry is about angles, but it can be put onto questions that are related to Pythagoras as well, so be careful of that. Our next topic to work through together is on circles, and we're going to be focusing on some circle theorems. I've selected some of the easier circle theorems to go through with you, so we're going to be focusing on 5 circle theorems. Before we do that, we've got to make sure that everyone feels comfortable with the circle vocabulary. So if we just look at the screen now, a circle is a set of points equidistant from its centre. And there are some key lines, and we can see here on the diagram we've got the circumference. The circumference is the outside of the circle, sometimes called the perimeter of the circle, the distance around the circle. We then have a really important point called the radius and the diameter. And the radius goes from the centre, as you can see here, to the circumference. And that can be drawn anywhere in the circle. You can go to any point on the circumference, it's going to give you the same value, the radius. The diameter is related to the radius. The diameter is twice the length of the radius. So if the radius was 5, your diameter would be 10. If your diameter was 20, your radius would be 10. So they have a relationship with each other, which you will know from finding the area and circumference of a circle. We then have further two words. One is chord, which is the line segment with 2 endpoints on a circle. So it doesn't go through the centre. It just touches the circumference in 2 points, and it splits them into 2 segments. And the last one is a tangent. Now this is this special line that's not actually inside the circle. You can see it, it's up here. This is a straight line that touches the circle at a single point, just 1 point. And it's sort of hard to see in this picture, but if we enlarged it, we'd be able to see it just touching the circle, and that's what we call the tangent. Some of these words are going to be in the circle theorems that we're going to be discussing. A few other words we have on the next slide. One is called arc. You can see the arc here is in orange. It's just part of the circumference, and it's like the arc, the curved part, just part of it. And when an arc is bound, so that's when the 2 lines coming in are the radius, so this one is a radius and this one is a radius, the bit in between is called a sector. Okay, so it's not a segment is just part of a circle. The sector is where you have the middle here, which is the centre, and these lines are radiuses. On this side we have the segment, which is a region bounded by a chord, which we had in the last slide, this one, and an arc just going across the 2. So a quick practice on that for you. You've got a circle, turn over the page, don't look back, and see if you can fill in the missing points to label this circle. I'm going to give you 1 minute to do it. Off you go. Our first one, we can take radius. The radius goes from the centre of the circle to the circumference. So here is our radius. Let's look at the diameter next. Next door over here, the diameter goes through the centre of the circle from the circumference on one side to the circumference on the other side. So this here is our diameter. This one up here is pointing at the edge of the circle, which goes all the way around, which is the circumference. In there. We have this small section of the circumference, which is the arc, and then the white part inside, which is this area bound by the arc, and a radius here and a radius here, which is our sector. So that's some of the key vocabulary that we're going to be using when we explain these circle theorems. In all of the circle theorems questions, you will be asked to calculate or work out a particular value of an angle that's missing. What you need to do is 1, work out the numerical value for the angle, but 2, you're going to have to explain why. And that's where you actually need to state the circle theorem. So this circle theorem says that the tangent, this line, meets the radius, this line, at 90 degrees. It's a rule. Okay, theorems are like Pythagoras' theorem, it's a rule. This rule states tangent meets radius at 90. So any place on the circle where you have a tangent and a radius, they're going to be at perpendicular to each other. That's like this, 90 degrees. That's circle theorem number 1. Our second theorem states that the angle in a semicircle, that's half of the circle, if you have the diameter going through the middle, this is the semicircle and the other side is a semicircle. So here, this angle is always 90 degrees. We could draw the triangle like this and it still would be 90 degrees. Anywhere along is going to be 90 degrees. Angles in a semicircle are 90 degrees. That's the second rule. So when someone's marking your paper, they'll be looking for the words semicircle and 90 degrees. The third theorem, the third rule, what I want you to learn is about the angle at the centre, this one. So we have a radius, and the centre is always double the angle at the circumference. And you can see that this angle comes from the same points, and this is 45. Say it the other way around, the angle at the centre is double the angle at the circumference, or the angle at the circumference is half the angle at the centre. Either way it works. So what you might have in the exam, this might be labelled, for example, 100, and they say, what's this angle? 50, or the other way around. The fourth circle theorem that's useful to know is angles in the same segment are equal. So this is your chord, which we learnt about a moment ago. Let me get another colour. This is your chord. The segment on this side, that's segment 1, and everything this side is segment 2. Any angle in there that's at the circumference, like here and here, are going to be the same. So the phrase is, the rule is, angles in the same segment are equal. The last circle theorem says that opposite angles in a quadrilateral add up to 180 degrees. This is a quadrilateral in a circle, okay? Not just any quadrilateral, a quadrilateral in a circle. You can see here that these ones, 113 and 67, add up to 180. And these two, let me get another colour, these two also add up to 180. So opposite angles in a quadrilateral add up to 180. That's a quadrilateral in a circle. Now, there are some other circle theorems which involve tangents and what's called the alternate segment theorem. These are the circle theorems, the 5 ones that I've pointed out that I want you to focus on for your revision around circle theorems. You've now got 2 sheets, 4 circles on each one. I want you to find the missing angle and I want you to state the theorem, so the rule as to how you found the missing angle. 2 sheets, I'm going to give you 4 minutes, off you go. So our first circle on the top left here, we have an angle here at the centre and we have an angle here at the circumference. You will remember that there is a rule that says angles at the centre is twice the angle at the circumference. That's the reason. So angle at the centre is twice the angle at the circumference. So in the centre here, if that's 74, the angle at the circumference is going to be half of that. So half of 70 is 35, half of 4 is 2. So this angle A is going to be 37. 35 plus 2, 37. Double 37, you get back to 74. This one here, this line across here, which you can't see, is the chord. That's splitting the circle into two segments. Angles in the same segment are equal. That's a circle theorem. So if that's 48, B has also got to be 48. Write down angles in same segment are equal. That's going to get you your 2 marks. Angle, reason. Let's look at this one here. We've got a 4-sided shape. It's a quadrilateral inside a circle where all of the points touch the circle. These are opposite angles. Opposite, write all of this down if you haven't done already, opposite angles in quadrilateral add up to 180 degrees. So if this one is 77, our missing angle here is going to be 103. Both of those angles adding up to 180. Our next one has 2 combined ones. So let's look at G to start with. G's in the centre, 36 is on the edge. It's the same one as this one here. So restate the reason. So G is going to be double whatever the angle at the circumference is, which is 36. 2 36s, well 2 30s are 60 and 2 6s are 12. So G is going to equal 72. We then have F over here. So on this one, we have the same as our second one. This is a chord, this is a segment, this is in the segment, and this is in the segment. So these two are going to be equal. So F equals 36. Why? Angles in the same segment are equal. Let's have a look at the next one. Here we have only one angle labelled. This angle is COA. COA. O's in the middle, that's where the angle is. We know this one, you can find out this one. It's half of what's in the centre. So half of 168, so 168 divided by 2. Well, we know half of 100 is 50, half of 60 is 30, and half of 8 is 4. Add those up and we're going to have 84. So we know this angle is 84. Then we can find another angle because this shape here, change my pen, this shape across here is a quadrilateral. If that's 84, the angle over here, they're going to add up to make 180. So our missing angle here is going to be 96. So 2 angles there, 2 different reasons. And let's have a look at our last 4 together. So we have a shape inside the circle on this one, which is the quadrilateral, but we also have this outside. Now, ABC is a straight line. Angles on a straight line add up to 180. So if that's 81, this one is going to be 99. If we know that's 99, then we can find this one out. Because it's a quadrilateral, it adds up to 180, so that's going to be 81. Looking on this side, we have the diameter. The diameter cuts the circle into 2 semicircles. So this side is a semicircle. The rule states angles in a semicircle are 90 degrees. So this one has to be 90. If that's 90 and that's 58, add them up, we have 148. All 3 of these angles It's a triangle, must add up to 180. So our missing angle here will be a 180, subtract 148, which is going to give us 32. So our missing angle here is 32. And our last two, we've seen this one before. We've got 41 at the edge on the circumference, and this one is going to be double. So double 41 is going to give us 82. Reason, angles at the centre are twice the angles at the circumference. This one we've seen already. Straight line across here. It's a chord. Two sides, segment. Angles in the same segment are equal. If that's 63, this has also got to be 63. So angle ACB equals 63. So each one of those, you need to state the rule and the actual angle working out. And I'd advise you as your first step to circle theorems to learn the 5 that I've gone through and then to progress to some of the more advanced ones at a later stage. So it's now time for you to take the final assessment in this series, which is the shape assessment. Press pause on the DVD. You have 10 minutes to complete the shape assessment. Good luck.